Hello, and welcome to the Sleepy Voyager. Before we drift into the dark between stars, take a moment to subscribe and tap the bell. It's a small click for you, but it helps this sleepy journey continue, night after night. When you're ready, settle in, breathe deep, and let's begin the countdown to contact. Night operations at an observatory are careful and methodical. The building stays dim with red lights so people can see without ruining their night vision. The air is cool to keep instruments stable. Computers, sensors, and cooling systems run continuously. Staff speak quietly so they can hear alarms or prompts. Chairs, notebooks, and checklists are set up before observations begin. Coffee and water are nearby, but food stays away from equipment. Safety rules are simple. Move slowly, watch cables, protect the optics, and never shine white light toward the telescope. The telescope sits on a heavy mount that can move with high precision. It points by reading encoders that track position down to tiny fractions of a degree. Motors are smooth and strong so the scope can follow a target as the Earth turns. When the dome slit opens, the inside air meets the outside air. The goal is to match temperatures to reduce turbulence around the telescope. Fans help equalize air and sweep away warm pockets. A stable dome environment means sharper images and fewer data problems. Before observing a target, the team calibrates. They take bias frames to record the camera's electronic baseline with zero exposure time. They take dark frames to measure the sensor's heat noise at the same exposure time as their science images. They take flat-field frames to correct for dust and uneven lighting across the detector. These calibrations let software remove fixed defects and reveal real signals. Each frame is saved with time, temperature, exposure settings, and equipment notes so it can be matched correctly later. Focus matters. The team adjusts focus by tiny steps and takes short test images. They measure how tight the star images are, using a value like FWHM and full width at half maximum. Lower FWHM means sharper focus. They also check the seeing, which is the atmosphere's blurring effect. Good seeing can make a small telescope perform like a larger one for that night. If the seeing is poor, they choose longer exposures or adjust expectations for data quality. The telescope needs a reference star to guide on. A guide camera watches that star and sends corrections to the mount. These corrections keep the target centered on the sensor during long exposures. Without guiding, stars can smear and faint signals can disappear into noise. Good guiding shows up as steady plots with small corrections in right ascension and declination. If wind gusts or cables pull, the guiding graphs will show sudden spikes and the team will fix the cause. Weather is monitored at all times. A station tracks wind, humidity, temperature, and cloud cover. High humidity risks dew on optics. Clouds reduce signal and change background levels. Wind can shake the telescope. Lightning and rain trigger automatic safing, which closes the dome. If conditions change, the schedule changes with them. Night work is flexible by design because the sky does not follow plans. Data arrives as images or spectra. Image data is a grid of pixel values. Spectral data spreads light into wavelengths so you can see chemical fingerprints. Raw images include background glow from the sky, sensor noise, and small defects. Software subtracts bias, subtracts darks, and divides by flats. It then aligns and stacks images to increase the signal-to-noise ratio. Stacking is simple. Real stars and comets line up and add together. Random noise does not. This makes faint objects visible that a single frame would miss. Timestamps are important. Each exposure is tagged with accurate time from a synchronized clock. For moving targets, timing tells you where the object should be in the next image. For changing targets, timing tells you when the brightness changed. The time, the pointing coordinates, and the exposure settings form the backbone of the observation log. If something looks odd later, these records let you trace the cause. The control room uses several screens. One shows the sky map with the planned path for the night. One shows live images. One shows guiding graphs, another shows system health, temperatures, voltages, and storage space. A terminal window logs events like bias saved, slew complete, and guiding locked. People keep notes by hand as well, because quick human notes can capture decisions, small problems, or observations about clouds and wind that the system does not record. Sensitivity depends on more than telescope size. Clean optics, good focus, steady guiding, low sky brightness, and careful calibration all add up. Even small gains matter when you are measuring faint changes in brightness of a distant object. The team checks histograms to make sure exposures are long enough to rise above red noise, but not so long that stars saturate. If a bright star is near the target, they adjust framing to avoid artifacts like blooms or ghosts. The first science exposures are conservative. Short tests confirm that the target field is correct. The team compares the star pattern in the image with a star catalogue on screen. If the rotation or scale is off, plate solving software calculates the exact pointing and sends a correction. Once the field is confirmed, they start the planned sequence, a set number of exposures with fixed times, or a repeating block with filters cycling through. Filters select wavelength ranges such as broadband for general imaging, or narrowband for gases that glow at specific lines. Noise has patterns. Certain pixels are hot, some columns flicker. The calibration files mark these issues so the reduction pipeline can handle them. Sky background changes with airglow, moonlight, and thin clouds. The team tracks the background level between exposures. If it rises, they shorten exposure time or pause. If it falls, they make use of the darker window. Simple graphs of background versus time help make quick decisions. Communication is direct and simple. One person calls out guiding stable, another says focus locked, someone else says humidity at 62% heaters on. No long speeches. Clear updates help everyone share the same mental picture of the system. If a problem appears, like a drifting focus, a stuck filtered wheel, or a dropped frame, the group follows a checklist. Most issues have known steps: pause exposure, park filter, reinitialize, verify, resume. The goal in this phase is clean, repeatable baseline data. You want to know exactly how the system behaves when nothing unusual is happening. That way, when a subtle change does occur, you can trust it. A small rise in brightness in the right part of the image may be the first sign of your target. A gentle curve in a light curve might be real. Confidence comes from preparation, not from dramatic moments. Quiet runs produce trustworthy results. For a visitor like 3I/ATLAS, motion relative to background stars is the key clue. The comet will shift slightly between exposures. Software can track and stack along the predicted motion to make the comet sharper while the stars blur, or it can track the stars and let the comet trail. Doing both views helps. One confirms the target, the other measures the sky. Accurate rates come from orbital models, but the camera confirms them in the moment. Throughout the night, backups run, data writes to fast local storage, then copies to a second drive or a network server. A checksum verifies that files are intact. Losing an exposure is not fatal, but losing a series can break a measurement. Power protection and surge suppression reduce risks, and generators stand by for outages. Reliability is part of the science. Good habits remove excuses later. Nothing here is magical. It is a chain of small, careful steps. Keep the optics clean, keep temperatures steady, calibrate often, focus precisely, guide steadily, watch the weather, log everything, review images as they arrive, adjust as needed, but avoid constant changes. Let the plan carry the work and let the data show you when to adapt. This approach is simple to describe and powerful to practice. As the minutes pass, the system reaches a steady state. The dome is open to the exact width needed. The telescope tracks smoothly. The guide star holds its mark. The camera exposes, saves, and resets on a predictable rhythm. The reduction pipeline keeps up. Monitors show flat lines where flat lines are good and so. Small changes where small changes are expected. The team watches, notes, and keeps the environment calm so the first real signal has the best chance to stand out when it arrives. It arrives from outside our solar system on a one-time path, a line that never closes into a loop. That is what makes it a visitor without a return ticket. In simple terms, it is moving too fast and on the wrong kind of path to ever come back. Most comets and asteroids the Sun captures follow ellipses, big ovals that bring them around again and again. This object follows a hyperbola, an open curve that comes in, swings by once and leaves forever. If you measured its shape with a single number called eccentricity, you would get a value greater than 1, and that is the signature of a traveller from elsewhere. Long before it reached our neighbourhood, it already carried extra speed, what astronomers call hyperbolic excess velocity, meaning even the Sun's gravity cannot pull it into orbit. It will visit, it will pass, and it will continue into deep space. Its temporary name reflects two things: order and origin. The number marks it as the third interstellar object identified passing through our solar system. The label after the number tells you who first saw it. A wide-field sky survey designed to notice faint, moving points against a backdrop of stars. Those survey telescopes scan the sky many times each night, looking for anything that shifts position in just the right way. Software compares fresh images with older ones, subtracts the fixed star field, and flags dots that move between frames. Most of the time, those dots are ordinary near-Earth asteroids or known comets. Once in a rare while, the motion and speed suggest something unusual. Follow-up observations confirm the path, and the object gets the interstellar designation that separates it, clearly and permanently, from local residents. Understanding its visit starts with simple geometry. Imagine the Sun at the centre, and the object's path as a shallow curved line cutting across the plane of the planets. There is a closest approach point called perihelion, where it receives the most sunlight and, if it has ices, shows the most activity. Before perihelion, it is inbound and faint, still far from us and lit from the side. After perihelion, it is outbound and often easier to see for a short time, because the geometry can place it closer to Earth and at a better phase angle. The Earth itself moves, so our viewing angle changes day by day. This creates small windows when the visitor is well placed in dark skies, and other times when it sits too near the glare of the Sun or too low on the horizon. The entire opportunity is measured in weeks or months, not years. Speed is the second key. Local comets approach a few tens of kilometers per second relative to the Sun. Interstellar visitors often arrive with a little more because they carry velocity from a different star's neighbourhood. That extra speed means everything happens quicker. The object crosses a degree of sky in hours, not days. Tracking and guiding must be tuned to follow that motion. Exposure times must balance two needs: long enough to collect light, short enough to avoid smearing the target into a streak. Teams will sometimes take two sets of images, one aligned on the stars to measure the backgrounds and one aligned on the moving object to measure its brightness and shape. By comparing both, they can separate faint signals from the general sky glow. What you can learn depends on what the object is made of and how it behaves. If it is rocky and dry, it may remain a sharp point of light, like a small, fast asteroid. If it contains ices, sunlight can warm it enough to produce a coma, a cloud of gas and dust surrounding the nucleus. That coma scatters sunlight and can grow a tail that points away from the Sun, pushed by radiation and the solar wind. A coma helps by making the object brighter, but it also complicates measurements by adding a fuzzy, extended shape that changes with time. Spectrographs can split the light to look for signatures of common gases like water, carbon monoxide or cyanogen, and for sunlight reflected by dust grains. The presence and strength of those signatures tell you about chemistry formed under another star's conditions. The name visitor without a return ticket is not poetic exaggeration, it is a practical constraint. Because it will not return, there are no second chances. Observers around the world coordinate to share time, weather, and longitude. When it sets for one observatory, it is rising for another. Southern and northern sites trade coverage as the path crosses the sky. Large telescopes gather spectra, while smaller, numerous ones monitor brightness over long stretches of time. Amateurs with good equipment contribute precise positions that refine the orbit. Every measurement feeds into updated predictions. Where to point tonight, how fast to track, which filters to use, and how faint the object may be in the next window. The orbit tells a story about origin. An interstellar object's incoming direction on the sky, its radiant, can be compared with the motion of nearby stars and our galaxy's general flow. If its path roughly matches the local standard of rest, it might have drifted for a very long time between stars. If it arrives from a specific moving group, it could have been ejected from a young system not far from us in galactic terms. Ejection happens when a small body passes close to a giant planet or through a crowded, changing disk around a newborn star. A small gravitational nudge in the right place can push it over the escape threshold, sending it into the interstellar medium as free debris. Over millions of years, these objects become seed stories travelling through space, pieces of other solar systems sampling ours. Brightness changes are more than aesthetics, they are diagnostics. A steady, periodic variation may indicate rotation, with different faces reflecting different amounts of light. A sudden change can mean a burst of activity, a jet turning on, or a fragment shedding. By measuring a light curve, brightness versus time, researchers estimate rotation period, elongation, how stretched the body is, and surface variations. If the object is very elongated and tumbling, the light curve will show complex patterns rather than a clean repeating cycle. If there is outgassing, you might also see a small push that slightly alters the trajectory, called a non-gravitational acceleration. The sign of that push helps distinguish gas jets from other forces and must be included to predict the path precisely. Distance limits the detail we can see, so scale is inferred. The absolute magnitude, which is how bright the object would be at a standard distance, sets a rough size when combined with an assumed reflectivity, albedo. A dark, coal-like surface reflects little light and would mean a larger object for the same brightness. A brighter, icy surface reflects more and would mean a smaller object. Without direct imaging, there is a range of possibilities. Thermal observations in infrared can narrow that range by measuring emitted heat, but those require the object to be close enough and the instruments to be available at the right times. Safety questions come up naturally. Is there a risk to Earth? The answer is simple for this kind of visitor. The path is known and fast, and the closest approach distances are large compared to any danger. The public can relax and simply enjoy the idea that something from another star is passing through our skies. For observers, the main risk is missing the chance because of weather, daylight, or a conflicting schedule. Once it moves beyond reach, it will fade below the limits of even major telescopes. Then it will be a set of numbers and a memory, continuing on into the dark with only our records left behind. Paperwork and naming conventions may seem dry, but they help everyone stay synced. The designation records discovery circumstances, positions and times. The official circulars announce updates to the orbit and to reported activity. Light curve databases collect rotation measurements, spectral repositories store line detections. All of this makes the object accessible to any team that wants to contribute. The result is a distributed global project that can form in days. One side of the planet measures colour, another side measures motion, and together they form a composite picture of a thing we may never see again. Children and adults can understand the key idea with a playground analogy. Imagine you're spinning in place and you toss a small ball lightly. It falls back near you and can be picked up again. That is like a normal comet on an ellipse. Now imagine a stranger runs past and throws a ball very hard across the playground. It cuts through your circle and keeps going. That is like an interstellar object on a hyperbola. You may touch it for a moment as it passes, but you cannot make it stay. The sky works the same way, only with gravity and starlight instead of hands. For many on the observing teams, the appeal is exactly that one-time nature. It asks for focus, cooperation, and respect for the clock. It reminds you that our solar system is not isolated. It sits in a larger neighbourhood where objects exchange places over long spans of time. Dust and ice formed around other suns can drift here and reflect our sunlight back to us. When you look at that faint dot on a screen and know it crossed the emptiness between stars, you're not just taking a picture, you're measuring a brief meeting between two planetary systems, a small shared moment written in motion and light, and you give it your best attention because that is all any visitor without a return ticket can fairly ask. Comet's visible glow is not the solid body itself, but the atmosphere it makes when sunlight wakes the ices near its surface. The nucleus is small, often a few kilometers across, cold, dark, and covered in a crust of dust and processed grains. As it nears the sun, different ices begin to sublimate at different distances. Carbon monoxide and carbon dioxide can drive early activity beyond 4 or 5 astronomical units, while water ice becomes the main engine inside roughly 3 AU. Gas escapes through pores and cracks at a few hundred meters per second up to around a kilometer per second, dragging dust with it. This outflow inflates a temporary atmosphere called the coma, which can grow to tens of thousands of kilometers across, dwarfing the nucleus by factors of 10,000 or more. In images, the coma looks like a soft, luminous ball. In data, it's a mixture of scattered sunlight from dust plus sunlight absorbed and re-emitted or fluoresced by gas species. Dust grains range from submicron smoke to millimeter bits. The smallest scatter blue light efficiently and can make a neutral blue hue, while larger grains give the warm tan fog many people picture. The overall brightness depends on the amount of dust and gas produced, on how quickly it's removed by radiation pressure and the solar wind, and on viewing geometry. At certain phase angles, the coma brightens because forward scattering puts extra light towards us. The gas component is chemically rich but optically thin. Spectra commonly show CN near 388 nanometers, C2 bands in the green, C3 in the blue, NH/OH from photo-dissociated water, and sometimes a narrow sodium emission that can form its own faint tail. In the near-infrared, lines of CO and CO2 trace volatiles that sublimate even in the outer solar system, while forbidden oxygen at 557.7 nanometers hints at water breakdown products. The dust and gas don't expand the same way. Neutral gas flows roughly spherically at first, then gets ionized by sunlight and swept into a long, straight, bluish ion tail that points almost exactly away from the sun, along magnetic field lines in the solar wind. Dust, being heavier, and only pushed by a sunlight's radiation pressure, follows curved paths that depend on grain size. Tiny grains get shoved hard and arc into the classic broad dust tail. Larger grains lag and can make a trail along the orbit. On some nights, geometry produces an anti-tail that seems to point toward the sun, a line-of-sight effect from the sheet of larger, slowly diverging particles. The coma's surface brightness often drops roughly like 1 over a rho with distance from the centre, if production is steady and outflow is constant, so observers measure profiles to test how smoothly the comet is breathing. Photometry uses concentric apertures to separate the bright inner coma from the outer halo, converting counts into standardized colors and into the AFO parameter, a simple proxy for dust production that multiplies albedo A, filling factor F, and projected aperture radius ρ. If AFR rises with time, dust production is increasing. If it falls, the coma is thinning or grains are getting coarser. Polarimetry adds grain physics. The coma's polarization curve versus phase angle reveals whether particles are fluffy aggregates or compact glassy chips, with a characteristic negative polarization dip at small phase angles caused by coherent backscattering. Close inspection of the inner coma often shows jets, collimated fountains from active vents that rotate with the nucleus to draw spirals or fans. When the spin axis tilts toward the sun, one jet can dominate and sculpt the coma asymmetrically. When multiple vents switch on and off with day-night cycles, the coma flickers with gentle periodicity. Jets act like thrusters, adding tiny non-gravitational accelerations that subtly bend the orbit. Modelers must include these forces to keep predictions accurate, especially for small, light nuclei. Dust-to-gas ratio matters for both physics and appearance. Gas-rich outflow builds bright ion features and strong molecular bands. Dust-rich outflow glows by reflected sunlight and can hang on as a golden fan even when gas lines are weak. Grain speeds depend on size and drag. Micron grains can leave at hundreds of meters per second, while millimeter grains creep out more slowly, settling into a trail that marks the comet's path. Thermal skin depth, the depth to which a day-night heatwave penetrates, is only centimeters, so surface layers cycle through freeze and thaw each rotation, sometimes sealing vents with refrost and sometimes cracking them open. Pressure under a sun-warmed crust can build until it vents explosively, producing outbursts, sudden brightenings, fresh jets, and newly ejected fragments that briefly spike the light curve. The coma is also an electrical and chemical reactor. Ultraviolet sunlight breaks molecules apart, creating radicals that glow in characteristic bands. Ions feel the interplanetary magnetic field and can kink or disconnect their tail when the solar wind shifts, causing dramatic tail events. Meanwhile, sunlight charges dust grains. Near the nucleus, the competition between gas drag, gravity, and electrostatic forces helps decide which grains escape and which settle back as a refractory mantle that darkens and insulates the surface. Observationally, separating all these pieces is a matter of technique and patience. Narrowband filters isolate C2, Cn, OH to map gas jets. Broadband filters measure dust color. Spectroscopy resolves lines to estimate production rates in molecules per second. High-cadence imaging tracks spirals to infer rotation period. And synchronous/Syndyne modeling, Finson-Probstein, matches dust arcs to grain sizes and release times. Even small telescopes can contribute by measuring the growth of the coma in arc seconds, the evolution of AFIU, and the nightly change in color index, while large facilities add high-resolution spectra and inner coma structure. For an interstellar visitor, the coma doubles as a messenger from another protoplanetary disk. Volatile ratios like CO/H2O or CO2/H2O and isotopes can hint at formation temperatures and irradiation history far from our sun's nursery. If the coma's spectrum lacks certain common bands or shows unusual ones, that difference becomes a data point about diversity among planetary systems. And because the coma is transient, shaped by real-time sunlight and rotation, it functions as a live experiment. Change the heliocentric distance, change the subsolar latitude, change the gas flux, and the laboratory rearranges itself. What we see as a soft glow is, in practice, a set of precise clues. Brightness gradients, line ratios, polarimetric angles, tail curvature, jet morphology, all of which, when read together, describe dust, ice, and light learning to speak the same language under the sun. The room learns to breathe with the cadence of the instruments, a quiet metronome set by exposure timers, guiding loops, housekeeping pings, and the slow rise and fall of graphs that look like sleeping pulse lines. Each countdown on the screen is a small promise. 29 seconds, 28, 27, a soft descent toward the next frame, the next measure of the night's heartbeat. When the shutter opens, silence flows in. When it closes, numbers flow out. That rhythm becomes the way everyone thinks. You pour tea between exposures. You check focus between guiding corrections. You glance at the sky brightness between calibrations. Soon the whole place keeps time with the same low drum in the background, as if the comet, the telescope, and the atmosphere have agreed on a tempo. The heartbeat is really many heartbeats woven together. There's the exposure cadence, how often the camera drinks light. There's the guide cadence, how often the mount listens and nudges. There's the telemetry cadence, temperatures, voltages, and fans reporting in at regular intervals. There's the human cadence too, eyes sweeping left to right across monitors, fingers tapping a notebook margin, a quiet voice sharing a number every few minutes. When all of these align, you feel it as ease. When one slips, the others tighten to catch it. A gust bumps the guiding star, the graphs quiver. Someone reduces exposure time, the sequence keeps its shape. The night doesn't ask for perfection, only for steadiness, the kind you could set a clock by. Counting down frames is not just waiting, it's sculpting signal out of noise with time as the chisel. Light is sparse when objects are faint, so you collect it in repeated sips, stack them, and let the randomness cancel while the real thing accumulates. The trick is to keep the cadence clean. If you miss a beat, the stack records the gap. If the rhythm jitters, the combined image shows it as a blur. So the team tends the intervals like gardeners tending rows, evenly spaced, evenly watered, evenly watched. A good sequence is beautiful in a plain way. Timestamps that step forward without surprise, exposure lengths that match within a second, sky backgrounds that drift gently rather than lurch. You can glance at the log and feel whether the night has a smooth pulse or an irregular one. Behind every countdown is a clock, and behind every clock is a standard. The computers sync to an atomic time source so that each exposure carries a timestamp you can trust to fractions of a second. For moving targets, those fractions matter. A small shift in time is a small shift in position, and a small shift in position is the difference between a dot and a smear. Later, the timestamps are translated to the solar system's barycenter, the common balance point of all the planets, so that any periodic signal is measured in a frame where the sun's pull and Earth's motion don't add a wobble. That correction is invisible at the telescope, but in the analysis it straightens lines that would otherwise bow. Timekeeping is invisible scaffolding. The building stands properly because the scaffolding was aligned. The heartbeats show up in images, but they sing clearest in plots. You take the brightness of the target in each frame, subtract the background, and divide by the combined brightness of a few steady reference stars. That gives you a light curve, the simplest and most honest record of what the sky did while you were watching. If the curve hums along flat within the error bars, the comet is quiet and your system is stable. If the curve rises slowly, a jet may be turning the nucleus dayside toward you. If it ripples with a period, the body may be rotating. If it stumbles, you look for clouds, guiding hiccups, or a thin moonlit haze that walk through the field. The curve tells you what the night felt like, but with numbers. Noise is never just one thing, so the heartbeat must be filtered thoughtfully. There's shot noise from the small number of photons, read noise from the camera and electronics, scintillation from the atmosphere, a fast twinkle that makes even bright stars breathe, and slow drifts from extinction as the object sinks towards the horizon. You can't bully noise into silence, you match its time scale. Scintillation dances frame to frame, so short exposures and larger apertures tame it. Extinction drifts over tens of minutes, so you fit and remove a gentle slope. Guiding errors spike with wind, so you flag and downweight those points. The goal is never to make the curve perfect, it's to make it honest about what is random and what is real. Choice of cadence sets the kind of heartbeat you can hear. If you sample too slowly, fast changes, alias into patterns that aren't there. If you sample too quickly, you collect a forest of noisy points without a clear line through them. The sweet spot depends on how the object behaves and how the sky cooperates. For an active comet, you might choose a few minutes per frame to follow gradual trends and occasional outbursts. For a tumbling shard, you might need seconds to catch rapid flickers. Between science goals and seeing conditions, you choose the beat that gives the signal its best chance to rise above the floor. Even the way you measure brightness has its own rhythm. You set an aperture around the target, large enough to catch the coma's light, small enough to avoid adding sky noise. Then you set an annulus around that to estimate the background, careful to avoid stars. The same sizes are used frame after frame so the measurement is consistent. If the seeing broadens, the aperture must expand or you'll clip the light. If the seeing sharpens, the aperture can shrink to lower noise. Some teams fit a point spread function. Some stick to fixed apertures. Either way, the cadence of how you adapt is recorded in the notes, so that later you know the adjustments were systematic rather than improvised. There's a heartbeat in position too. The target shifts across the detector as the Earth turns and as the comet moves. Centroiding algorithms measure that shift to a fraction of a pixel. If the motion matches the predicted path, confidence builds. If the motion walks a little faster or slower, you recalculate rates and update the tracking. If the motion kinks, you consider non-gravitational nudges like asymmetric outgassing acting as a tiny thruster. A position time plot, simple dots in a straight line, is one of the most satisfying pictures an observatory can produce. It says, "We listened on time and what we listened to kept time with us." Everything that repeats invites a search for period, and periods are how heartbeats become meaning. You take the light curve and run a Lom's-Gargle periodogram to see which frequencies stand out above noise. Peaks suggest rotation or recurring geometry from jets sweeping around. Wavelet transforms show how those frequencies grow or fade through the session, revealing whether the rhythm is steady or evolving. If two close peaks appear, you may be watching a nucleus with two principal axes of rotation, a slow tumble rather than a simple spin. The statistics cannot guarantee you a heartbeat, but they can tell you where to lean your ear next. Calibration frames have their own quiet pulse, woven between science exposures. Every so often you insert a short focus run because temperature drift can move the best focus by microns that matter. You check a standard star to keep photometric 0 points honest as the night's transparency slides. You recenter the guide star when the field rotates or the mount crosses the meridian. Each small interruption is purposeful, each small adjustment is logged. The sequence breathes. Inhale light, exhale corrections, inhale again. From the outside, this can look like button pressing, but inside it feels like listening. You learn the particular tempo of each instrument, the camera that returns its frames in a smooth, even stride, the filter wheel that clicks and settles in precisely the same number of seconds, the mount that hums at a constant pitch when the wind is below a threshold and at a slightly higher one when it climbs. You learn the tempo of the sky, how quickly the background rises when the moon lifts, how slowly the seeing recovers after a gust, how thin clouds announce themselves as a gentle swelling in background before they are visible by eye. You're not predicting the future so much as aligning with it, one beat at a time. Redundancy keeps the pulse true. 2 reference stars instead of 1, 2 temperature sensors on the camera body, 2 independent clocks cross-checking times, 2 copies of the data written to different media, with checksums verifying each transfer. None of this changes the light itself, but it protects the rhythm from the small accidents that would otherwise throw it off. If a drive hesitates, the other catches the frame. If a reference star turns out to be variable, the second holds the baseline steady. A clean heartbeat is not fragile, it's a rope made of many small threads. The mind enters the same pattern. Distractions get filed between exposures. Decisions happen at the ends of countdowns. You commit to the next block of frames and let them run, resisting the urge to tweak every minute. Patience is not passive here. It's an active choice to maintain cadence. In that choice lies the difference between a scattered night and a useful one. You can feel the temptation to chase tiny changes, but the curve rewards restraint. If a change is real, it will persist into the next beat. If it's noise, it will fade like a ripple that forgot its source. And then there is the most direct heartbeat of all, the photon counter inside the camera, ticking as quanta arrive. It does not care about our schedules, our drafts of the night, our ideas about what should be happening. It only adds 1 each time light lands. That count is the oldest music, the one any detector recognizes. We build our cadences around that steady rain so that when something in the sky increases the rate, by rotation, by jet, by geometry, we recognize it as the change in the song rather than a fluke. The counters tick, the frames accumulate, the plots thicken their lines, and the night, kept carefully in time, continues to offer up its slow, precise pulse. Gravity writes in curves, and we read those curves as orbits. The simplest description uses 6 numbers, The classical orbital elements, which together tell you the size, shape, tilt and alignment of the path, plus where the object is along it at a chosen instant. The semi-major axis measures size for bound ellipses, but for a one-time visitor on a hyperbola, we talk about the semi-major axis as a negative number whose magnitude sets the energy. The eccentricity tells you the shape. 0 is a circle, between 0 and 1 is an ellipse, exactly 1 is a parabola, and greater than 1 is a hyperbola that never closes. Inclination is the tilt relative to the ecliptic plane. The longitude of the ascending node marks where the path crosses that plane going north. The argument of perihelion sets where, along the orbit, closest approach to the Sun occurs. Finally, the mean anomaly, or equivalently time of perihelion, says where the object is at a specific epoch. With just these 6, plus a standard solar mass and coordinate frame, you can propagate positions into the past or future, and know where to point a telescope. Under the hood, 2 conservation laws carry most of the meaning: energy and angular momentum. Energy fixes the size and openness of the path. Angular momentum fixes how close the object can swing to the Sun for a given speed. The Vis-Viva equation connects speed VVV, distance RR, and semi-major axis AA through V squared equals mu, open parenthesis 2 over r minus 1 over a close parenthesis, V squared equals mu, open parenthesis 2 over r minus 1 over a close parenthesis, where mu is the Sun's gravitational parameter. For a hyperbolic interstellar object, a less than 0 and the term 1 over a 1 over a is negative, leaving a non-zero speed even far away, the hyperbolic excess velocity of infinity. That leftover speed is the object's accent, the part of its motion not picked up or lost to the Sun, evidence that it began its journey bound to another star and was ejected. Positions on the sky are measured in right ascension and declination against a fixed star catalogue tied to an inertial frame like ICRF/J 2000. Each measurement is an astrometric point with an uncertainty ellipse that depends on seeing, pixel scale, and centroiding quality. Collect enough of these points over hours and days, and you can solve for the 6 elements with least squares methods. The residuals, the differences between observed positions and computed ones, tell you if the model fits within expected noise. Systematic residuals that curve one way suggest that timestamps, station coordinates, or star catalogue biases need checking. Residuals that change when the comet brightens can hint at non-gravitational forces from outgassing nudging the trajectory. Time is part of the language. Observations are corrected for light time delay, because what you record is where the object was when the photons left it minutes ago, not where it is now. They're also corrected from the rotating Earth to the solar system barycenter, so that daily and yearly parallax do not masquerade as orbital features. The difference is noticeable for nearby or fast movers. A visitor crossing several arc minutes per hour can show measurable parallax between observatories on different continents, and that geometry actually helps nail down distance and direction of motion. Accurate mid-exposure timing matters. When exposures last a minute or more, the recorded position is effectively an average across that interval, unless you account for the object's motion on the detector. Once you have a preliminary orbit, you propagate it using numerical integrators that include the gravities of the major planets, the Moon, and sometimes large asteroids. For an inbound interstellar comet, Jupiter's pull is the main local sculptor. A slightly different closest approach distance to Jupiter in the past translates into a different radiant in the present. For many visitors, the planetary encounter is distant, and the path is essentially a straight hyperbola bent by the Sun alone, but you still include perturbation so that small errors do not grow into missed pointings. General relativity adds a tiny perihelion shift that is negligible for most comets yet included in high-precision ephemerides by default. Solar radiation pressure, acting primarily on small dust, is critical for particles, but is small for a kilometre-scale nucleus. Still, Asymmetric outgassing can act like a thruster, so you add Marsden-style non-gravitational parameters A1, A2, A3 aligned with the radial, transverse and normal directions to absorb that extra push if the residuals demand it. Different anomalies, mean, eccentric, true, are just different ways to talk about where the body is along its curve. Mean anomaly increases uniformly with time, which makes scheduling easy. Eccentric anomaly relates cleanly to the ellipse's geometry. True anomaly is the literal angle from perihelion as seen from the Sun, and is the most intuitive for visualizing where the comet is. For hyperbolas, the equivalents use hyperbolic functions, but the idea holds. One parameter ticks like a clock, another maps cleanly to the curve. Solving Kepler's equation bridges the clock-like parameter and the geometric one, turning time into position. Modern codes do this thousands of times per night while building ephemerides, and observers see only the outcome: pointing coordinates, rates of motion, and uncertainty ellipses. Uncertainty is part of every element. Early arcs, say a handful of measurements over one night, leave wide error cones that grow quickly into the future. Add another night, especially separated by many hours of Earth rotation, and the cone collapses dramatically. A week of coverage across different geometries turns guesswork into confidence. Orbit fitters publish covariance matrices that describe not just how uncertain each element is, but how those uncertainties are correlated. For planning, you propagate that covariance to the sky plane and get an uncertainty ellipse around the predicted position. Wide ellipses call for larger search boxes and shorter exposures to avoid trailing. Narrow ellipses allow tight fields and longer integrations. Tilt and orientation in code dynamics you can read at a glance. A low inclination places the path near the ecliptic. A high inclination can bring the object from far above or below the planetary plane. The longitude of the ascending node picks the intersection with the ecliptic. The argument of perihelion rotates the ellipse or hyperbola within its plane. These three define how the path threads through the solar system's disk. For interstellar objects, the incoming radiant is often compared against the local standard of rest and known stellar streams, to ask whether the visitor may have been ejected from a young moving group or has been drifting for eons, randomized by weak galactic tides and stellar encounters. Simple checks help classify a newcomer. The Tisserand parameter with respect to Jupiter, TJT_J, mixes semi-major axis, eccentricity and inclination into a number that, for solar system comets, tends to fall into bands associated with different source regions. Interstellar objects do not obey the same patterns, but a TJT_J, far from typical comet families, is one more sign you're not dealing with a standard Oort cloud returnee. The heliocentric specific orbital energy epsilon equals V squared over 2 minus mu over r, being positive everywhere is the crisp criterion for an unbound path. If your best fit epsilon stays positive even when you push the uncertainties, the visitor label is secure. The same mathematics that reads orbits can also pose transfer questions in reverse, like the Lambert problem. Given two positions and the time between them, what orbit connects them? Analysts sometimes use Lambert solvers on sequences of astrometry to get rapid initial orbits before refining with full least squares fits. Gauss's method and Laplace's method are classical first orbit tools too. 3 positions at known times produce a first guess for the state vector, position and velocity at a chosen epoch. From there, modern solvers iterate, downweighting outliers and folding in realistic force models. For observers, all this reduces to clear instructions on the whiteboard: where to point, how fast to track, what rate to subtract in software if we align on the stars, and how large the uncertainty box is. Rate and direction are given in arcseconds per minute along 2 axes. A fast hyperbolic visitor can cross the field quickly, so you might plan to offset ahead of the predicted position and let it drift into the center, repeating that pattern as the night progresses. If the uncertainty ellipse is long, you tile it with short exposures that sacrifice depth for coverage. If the ellipse is compact, you commit to deeper frames for better photometry and possible coma structure. Orbits are also stories about cause and effect. A slight change in perihelion distance alters peak heating and thus outgassing. Outgassing alters the non-gravitational parameters. Those parameters feed back into where the object will be on your next night. The language is recursive. Data update elements. Elements update predictions. Predictions guide new data. That loop can run daily when a visitor is bright enough for many teams to observe. Shared astrometry through central clearinghouses tightens the fit for everyone. Infrared detections add constraints on size and albedo. Spectroscopy adds constraints on activity drivers. Each discipline speaks a dialect, but the shared grammar is still the 6 elements evolving under gravity. Even for a sleep-gentle documentary, the takeaways can be plain. A path through space can be described by a small set of numbers. Those numbers change slowly under gravity and slightly under jets of gas. By measuring positions precisely and timing them accurately, we can predict where to look next and what we might see. The shape parameter greater than 1 means this is a once-only track. The incoming speed at infinity v infinity is the visitor's signature. The tilt tells us which hemisphere gets better views. The time of perihelion says when activity might peak. The uncertainty ellipse says how confident to be. When you see a clean match between prediction and image, a faint point appearing exactly where the element said it would, you're watching a sentence written in gravity being read correctly. One coordinate, one timestamp, one quiet confirmation at a time. Data arrives the way quiet snow does, flake by flake, frame by frame. Small pieces landing so gently you only notice the pattern after it starts to collect. Each exposure is one layer. On its own, it looks like static, a peppering of grey and faint salt-white points with a few bright spikes where a star or a hot pixel stands out. You don't force it to make sense, you let it build. The first rule is to keep every flake traceable. Files are saved with exact timestamps, pointing coordinates, exposure length, filter, temperature, and instrument settings in their headers. Checksums verify that what was written is what was meant. A backup runs while the next frame exposes. Nothing dramatic, just accumulation and care. The first pass through the snowfall is housekeeping. Bias frames remove the camera's electronic 0 point, the offset that makes dark read as not quite 0. Dark frames subtract the sensor's thermal patterns, the faint glow of heat that shows up as false light on long exposures. Flat fields divide out uneven sensitivity and dust shadows across the detector, so one corner doesn't pretend to be dim sky while another pretends to be bright. A bad pixel mask tags the few pixels that always misbehave so their oddities don't get mistaken for stars or fragments. After these steps, the field is still snowy, but it's honest snow. The randomness is mostly from the sky and the faintness of the thing you're trying to see. Next comes alignment. Even if the telescope tracks well, the stars shift by fractions of a pixel. Software measures their centroids and shifts each frame so the pattern lines up. If you're tracking the comet's motion instead, the stars will smear while the visitor sharpens. You can do both alignments and keep both products. One stack is on the stars to study the background and reference points. The other stack is on the target, so the faint coma or point can add up while the star field turns into soft streaks that won't trick your eye. Stacking is the heart of snowfall thinking. Real features add, random noise cancels, outliers get identified and set aside. Cosmic rays are easy to spot in a snowfall. They look like thin, bright scratches or tiny needles that don't repeat from frame to frame. Sigma clipping removes them. If a pixel is far from the median of the same pixel across the stack, it's an outlier and gets replaced by a reasonable value. The same trick tames airplane and satellite trails, which draw straight lines through the field in single images but vanish when you combine many. What remains after clipping is what repeats, and repetition is the quiet definition of reality in this kind of work. Once the images are clean, measuring becomes simpler. For a field with stars, you pick a few that don't saturate, measure their brightness with a circular aperture, subtract the local background measured in a surrounding annulus, and compare against catalogue magnitudes to translate counts into real units. For a coma, you use concentric apertures to see how brightness falls with distance from the centre. If it drops like 1 over a radius, production is steady. If it's steeper, dust might be settling or grains might be larger. If it's flatter, a jet might be filling the inner coma with fresh material. The numbers are dry, but the behaviour is not. It is a kind of breathing you can see. Difference imaging is another way to read the snow. You model the background, stars, faint galaxies, the static scene, convolve one image to match the seeing of another, and subtract. What's left is what changed or moved between frames. A comet popping slightly brighter, a jet curling from one side of the nucleus, a small piece drifting. These show up as tidy residuals on a plain grey canvas. The technique is forgiving of crowded fields and uneven transparency, and it gives you a direct look at change, which is the most informative part of faint things. Time series tools turn rows of numbers into shapes your eye understands. You plot brightness versus time for the target and for the reference stars. If they all rise and fall together, that's the sky changing. If only the target rises, that's your visitor. To keep the curve fair, you apply simple filters, median smoothing to suppress one-off spikes, low-order fits to remove slow trends from thin cloud or air mass, and careful flags for frames where guiding slipped or wind shook the view. You don't erase the story, you erase the smudges on the page so the story is readable. Frequency analysis is a way to ask whether the snowfall has a rhythm. A Lomsgargle peridogram tests a set of trial periods and asks which one explains the up and down best. If a clear peak appears, you can fold the light curve by that period and see whether the points climb smoothly from dim to bright and back. That pattern can indicate rotation or a repeating viewing geometry for a jet. If no period stands up to scrutiny, you accept that the object is either quiet, changing too slowly for tonight's window, or changing in a complex way that needs more data. In snowfall thinking, not yet is a valid and valuable result. Spectral data has its own kind of flakes, counts per wavelength bin, more scatter than it seems anyone could love, and faint lines that become believable when they appear in the same place across multiple exposures. You subtract the sky, including the narrow airglow lines. You divide by a standard star to remove the instrument's wavelength response. You correct for atmospheric extinction, which dims blue light more than red. What's left is the comet's fingerprint, broad dust reflection, and, if you're lucky, faint gas emissions. You integrate under the lines to estimate production rates. You compare ratios like Cn to C2 or OH to continuum to infer chemistry. You accept that some nights the lines are too faint to trust and that the right response is to add more flakes, not to guess. Machine learning can help, but it's less magic than discipline. A trained classifier can scan stacks for trails, cosmic rays or residual patterns and flag frames that need a second look. A convolutional net can detect faint moving points across noisy backgrounds by learning what motion looks like across consecutive images. A Gaussian mixture model can tease apart multimodal noise distributions when the sky background is non-uniform. These tools are assistants, not judges. They speed up triage so humans can spend time on interpretation, and they include uncertainty estimates so you keep your skepticism where it belongs. Compression and storage are unglamorous essential parts of snowfall. Lossless compression shrinks FITS files without throwing away information. File names encode time, filter, and sequence number, so sorting is visual, not a puzzle. A manifest logs every file written, every failure recovered, every checksum verified. Data lives on fast local disks while you work, then migrates to slower, safer storage when the session ends. When a future you wants to remeasure something, the path back to the original flakes is clear and short. Context frames your interpretation. You overlay the field with a catalogue to see which stars you're measuring. You check the moon's phase and separation, because moonlight raises the background and reduces contrast. You look at the phase angle Sun, Comet, Earth. because forward scattering can brighten dust and make an ordinary night look extraordinary. You consider heliocentric distance and geocentric distance because activity and apparent speed depend on both. The point is not to be fancy, it's to make sure your something happened is actually the comet and not the geometry of the snowfield changing under your feet. Quality control is a rhythm of simple checks. Plot background level versus time. It should drift slowly, not jump. Plot WHM of stars versus time. It should follow seeing and focus, not wiggle randomly. Plot the centroid of the target against prediction. It should stay close with residuals in line with measurement error. If any of these go sideways, you pause the pipeline and find the cause. Maybe frost has started to form and the heater needs a bump. Maybe the guide star is faint and needs replacing. Maybe thin cloud arrived and you switched to shorter exposures or a redder filter. The snow keeps falling, but you shape the drifts so they don't bury the signal. Communication keeps everyone aligned on what the snowfall is telling you. One person calls out, background up 20%, thin cloud likely. Another says, guiding RMS stable, 0.4 arc seconds. Someone else notes light curve up 0.1 magnitude over 30 minutes, references flat. Short, precise sentences turn the fog of many numbers into a shared picture. Notes in the log add small facts computers don't know. Zodiacal band visible. Faint aurora to the north. Nearby bright star out of frame after 2:15. These become gold later when you explain oddities in the data without guessing. When you finally make a figure for the night, a stacked image aligned on the comet, a difference frame showing a faint jet, a light curve with clear low noise points, it looks calm, almost too simple for the hours it took. That's the nature of snowfall work. The beauty is in how the simple picture was earned. Every flake landed in the right place. Every outlier was handled without fuss. Every step was small, reversible, well documented. You didn't demand a revelation. You invited one by keeping the field clean, the cadence steady, and the interpretation patient. And still, the most helpful habit is humility. A single point that doesn't fit may be the start of a new trend or just a wind gust. A faint structure in the coma might be a real jet or a residual from imperfect subtraction. You ask the same question each time. Does it repeat? Does it persist? Does it agree across methods? If yes, you keep it. If not, you set it aside without resentment and collect more. The sky rewards this temperament. The signals in the snowfall become letters, letters become words, and frame by frame the words begin to form a message simple enough to trust and strong enough to carry forward into the next night's quiet accumulation. When a visitor carries ice from another system, it carries weather reports from a star we will never see. Those reports are written in ratios and structures more than in pictures. The proportion of deuterium to hydrogen in its water, the mix of carbon-12 to carbon-13 in its carbon-bearing gases, the nitrogen-15 pattern in radicals like CN, the faint signatures of noble gases that only stay if the ice formed unimaginably cold. A high D/H ratio hints at formation in a deep freeze where heavy hydrogen was favoured. A lower one means warmer chemistry or later reprocessing. Carbon and nitrogen isotopes point to the blend of interstellar heritage and disk chemistry the grains encountered before they were glued into a nucleus. If the coma releases argon or neon in measurable amounts, it suggests ices that trap these reluctant atoms at temperatures so low that even sunlight near our distance from the sun will begin to free them. All of these numbers are simple once stated and difficult to obtain, and each one says, this is what cold meant where I grew up. This is how radiation worked in my nursery. This is how quickly warmth arrived and how long it stayed. The dust tells its own version. Under mid-infrared light, silicate grains announce themselves with broad features around 10 and 20 microns. The exact shape of those features hints at mineralogy, magnesium-rich olivines and pyroxenes, amorphous glassy components, and sometimes the sharper notes of crystalline grains that once felt temperatures high enough to anneal their structure. Finding crystalline silicates in cold comets means that, in some disks, hot material migrated outward, or cold material wandered inward and back again. The fraction of crystalline to amorphous content becomes a measure of how strongly a protoplanetary system stirred itself. Polarization curves across the coma reveal grain size and fluffiness. Aggregates of tiny monomers polarize light differently than compact chips knocked from bedrock. A fluffy aggregate means gentle, low-temperature assembly. A compact shard suggests brittle crust or collisions. When the dust is rich in complex organics, dark carbonaceous coatings often called tholins in the lab, the spectrum reddens and smooths, another echo of radiation chemistry acting over long spans in the parent system's outer reaches. Water, the main engine of familiar comets, arrives with quiet subplots. The ratio of ortho to para spin states in the water molecules has been used as a kind of spin thermometer, a snapshot of the conditions during formation or equilibration in ice grains. Though interpretations remain careful and contested, OH in the ultraviolet, a daughter of water broken by sunlight, gives production rates, but small deviations from standard models hint at masking by dust or extra sources like icy grains releasing water away from the nucleus. If carbon monoxide or carbon dioxide dominates the early activity far from the sun, that tells of volatile-rich layers near the surface. If water takes over late and strongly, the surface may have a dust mantle that delays heat. The handoff between these drivers, as measured by changing gas ratios with distance from the sun, becomes a small timeline of layers laid down in another system, and then edited by a slow life in interstellar space. Layering matters because a comet is not a homogeneous snowball. Thermal models expect an onion of histories, a processed crust at the top, more primitive ices below, pockets of clathrate hydrates that trap gases within water ice cages, and voids where sublimation has hollowed small caverns. As the visitor spins, sunlight moves the subsolar point and the heat wave seeps a few centimeters into the body with each day-night cycle. Amorphous water ice, if present from its native cold, can transition to crystalline form when warmed, releasing trapped gases in a modest burst that looks like a heartbeat in a light curve. Clathrates liberate their guests when the cages destabilize, often at temperatures that arrive before water itself is ready to flow. Each mechanism has a pacing and a preferred temperature, and when you watch the coma's composition vary with the object's rotational distance, you are seeing which locks are turning in the subsurface and in what order they were set, long before our sun's light ever knocked. The interstellar years leave marks that are subtle and cumulative. Cosmic rays travelling even through the thin shielding of dust and ice make new radicals, crack heavier molecules, and carve a patina of complex organics on the grain surfaces. This slow radiation cooking darkens the albedo, making the nucleus a charcoal lamp that glows only by reflected light. The depth of this processed rind versus fresher material underneath sets how quickly activity starts when warmth arrives. If fractures cut through the crust, gas pathways can bypass the oldest layer and vent like nozzles, producing jets that carry the chemistry of the interior to the coma in narrow, time-tagged streams. By taking spectra repeatedly as the nucleus rotates, you can watch these streams rotate into and out of view and read a compositional map across the nucleus without ever seeing its surface directly. Not all echoes are chemical, some are mechanical. The material strength of the nucleus, how easily it fractures, how much torque it tolerates before its spin state drifts, speaks to the way its building blocks were packed and cemented. A weak, porous body with high macroporosity suggests gentle assembly from aggregates, a testament to a disk where collisions could stick without shattering. A tougher, denser body hints at compression or sintering, perhaps a history of closer passages to its parent star, or longer residence in warmer zones before ejection. When outgassing torques change the rotation period measurably over days or weeks, you infer not just where active areas are, but how well the interior couples forces, another way to listen to the soundness of a structure raised far away. Ejection from the parent system is itself an archive. To leave, the object likely grazed a giant planet or felt cumulative nudges in a crowded young system until its energy turned positive. If its path into our neighbourhood aligns with known stellar streams, moving groups, or the local standard of rest, you begin to imagine its birthplace in the crowded nursery regions where planets form in company. If its incoming direction is uncorrelated, you accept a longer, lonelier crossing, randomised by weak stellar tides in the galactic disk. In both cases, the coma is the readable part. Volatile rich layers near the surface can survive only if the object was kept cold most of its life. A devolatilized crust suggests more heating episodes. Noble gas retention argues for very low formation temperatures or burial depths. Their absence can mean the opposite, or simply that detection limits were not met. The lack or presence of certain organics may reflect the UV field in the parent disk and the mix of interstellar and nebula chemistry it inherited. Some grains carry stories older than any star. Pre-solar grains, tiny specks of silicon carbide, graphite, or refractory oxides, have isotopic signatures plainly not made in our Sun, sometimes not even in a single supernova, but in red giant winds or novae. These grains are rare, but when found in cometary material, they remind us that disks are not blank slates. They remix the galaxy's leftovers. In remote observations, we cannot pluck grains from a visitor's coma, but we can look for spectral hints of unusual refractory components, for the slope of the continuum that suggests large organic mantles, and for polarization anomalies that betray exotic textures. Every indirect indicator is welcome because it says whether the parent system shredded and reassembled its solids vigorously, or let them drift largely unchanged into planetesimals. The solar wind writes over the message as soon as it arrives, and even that overwriting is informative. Ionized molecules in the coma align with the interplanetary magnetic field, building a thin, straight ion tail that can kink or disconnect when a magnetic sector boundary sweeps past. These disconnection events reveal how quickly the coma responds to changing space weather, and how much ion production is available to be sculpted. The speed and density of the ion flow, measured in high-resolution spectra by Doppler shifts and line widths, connect coma physics to heliospheric physics in a way that is the same for all comets, yet still coloured by the visitor's unique outgassing rates and composition. The dust tail, broader and slower, curves according to radiation pressure and grain size. By matching those curves with models, you back out ejection speeds and size distributions, numbers that reflect both surface cohesion and gas drag efficiency, again linking mechanics to chemistry to formation history. Observationally, the cleanest echoes are often the simplest. A colour index, how bright the coma is through a blue filter compared to a red one, shifts with dust composition and grain size. A rise in airfire, the dust proxy, without a matching rise in gas lines suggests a dust-rich burst, perhaps from a crust fragment collapsing and exposing fresh material without much volatile release. A steady CN band with declining continuum hints at gas production decoupled from dust, perhaps from icy grains sublimating farther out in the coma. Or a sudden sodium line flares, a rare but telling signal that alkali atoms are being liberated, which demands very specific conditions and speaks to the mineral mix near the surface. Each small behaviour is a question answered about the visitor's layers and their past. Even the geometry of light helps decode foreign sunlight. Forward scattering at certain Sun-Comet-Earth angles boosts brightness, and can make coarse, transparent grains glow more than they should. By measuring how strong that boost is across phase angles, you sketch the porosity and size of grains, and by extension the environment where those grains were grown. Thin, fluffy aggregates grown in gentle, low-speed sticking environments scatter differently than compact, glassy grains annealed near heat. This is kitchen table physics, how flour dusts the air compared to sugar crystals, but it scales up into a story about where in a disk the ingredients were mixed and baked. Instruments that catch the faintest lines turn a coma into a ledger. Radio receivers look for rotational lines of CO, HCN, H2, CO, CH3OH, each molecule a thermometer and clock for different parts of the chemistry. Near-infrared spectrometers watch vibrational bands of water, CO2, and organics against a thermal continuum that rises and falls with heliocentric distance. Ultraviolet spectrographs trace OH and atomic oxygen, letting you separate parent molecules from their daughters. When these are measured over time, especially through perihelion and beyond, the curves of production show which reservoirs were near the surface and which were buried, which were steady and which were gated by diurnal rotation. The pattern is not random, it is the parent system's layering written in our light. None of this requires us to assert a particular birthplace. The point is that a traveller's coma is a messenger that speaks in a dialect we have learned to pass from our own comets and from the debris we've sampled and studied. When the lines are faint or missing, faint and missing are still messages. Either the layers were poor in that ingredient, or the geometry kept it masked, or the instrument's sensitivity set a limit that becomes a boundary line for future work. When the lines are strong and the dust is bright, the echo's louder. It says, "The star that raised me offered these ices, this heat, this mixing, this pace of change." When we write down the ratios and the profiles and the simple brightnesses, we are not just filling a table, we are translating weather from another sun into numbers that any telescope in any epoch could understand. And after the traveller is gone, the records remain readable because they are written in common units. Molecules per second, magnitudes, microns, meters per second, degrees. Future visitors will add columns, and a small catalogue of other sun climates will grow. One may be CO-rich and dust-poor, another dust-rich and oddly depleted in familiar gases, a third surprising in noble gases or in its crystalline fraction. Together they will outline the variety of protoplanetary kitchens the galaxy runs. Each echo strengthens the map, and each map makes the next whisper easier to place, so that the next time an object from elsewhere begins to exhale in our light, we will hear not only that it is breathing, but also quietly and clearly how its first air once felt. Some messages arrive as shouts, most arrive as texture, a faint roughness on what should be smooth, a rhythm hiding inside randomness, a ratio nudging away from even. Learning to hear them means learning to prefer the almost to the obvious. You start by deciding what quiet actually is. Quiet is the distribution of background counts when nothing changes. Quiet is the colour index of a field on a moonless night. Quiet is the guiding correction when the wind is low. You measure that quiet again and again until normal is not a guess, but a shape you can draw, with a centre and shoulders you expect. Only then do you allow yourself to say that a small departure is not just mischief from the air or electronics. Only then do you let surprise enter the room. The first kind of quiet breaking is a texture change. A coma that should fall off smoothly with distance looks slightly lopsided. The inner few arc seconds, averaged over many frames, show a gentle plateau on one side, like breath favouring a single nostril. This could be a jet making a fan too weak to see in a single image. You test the idea the way you test any perhaps. Rotate through azimuthal wedges, compute profiles, watch for a repeatable excess that co-rotates with the nucleus. If the pattern follows the sky instead of the comet, it's instrumental. If it waxes and wanes with the object's light curve phase, it's probably real. Texture is shy, it answers only when asked in a steady tone. The next kind of quiet breaking is a ratio change. Dust scatters light differently at different wavelengths, and gases glow at specific lines. Take alternating frames and 2 filters and build a simple colour index through the night. If the index drifts redder, while overall brightness stays flat, grain size may be changing. Larger particles from a deep event, fewer small grains because sunlight is sweeping them faster, or a temporary surge of organics. If the index shifts in sync with the faint gas bands lighting up, it is chemistry, not dust. Ratios are kinder than raw counts because they cancel some of the atmosphere's mood. They are the whisper that survives when the room clears its throat. A third kind of quiet breaking is rhythm. Noise is forgetful, it does not keep time. If an up and down repeats with a period that survives different bin sizes, different subsets of data, and different ways of subtracting trends, you're watching something turn. Small bodies rarely rotate with clockmaker precision, jets modulate, geometry migrates, but even a soft peak in a periodogram can be enough to anchor a hypothesis you will test again tomorrow. The discipline is to avoid drawing faces in clouds. You guard against aliasing by keeping cadences that do not accidentally carve the night into multiples of the suspected period. You split the time series into halves and ask whether both halves hum the same note. You compute a false alarm probability and keep your pride still until that number sits comfortably low. Detection is a conversation between thresholds and priors. A low threshold for declaring something happened will discover many somethings and many phantoms. A high threshold will miss subtle truths. The prior, the picture in your mind of how likely a signal was before you looked, should be shaped not by optimism but by physics. An interstellar vista far from perihelion is less likely to change quickly than one near peak heating. A small nucleus with a history of outburst deserves a more watchful ear. Bayesian thinking is just a tidy way to say that you let what you already know modulate how loudly a small hint must speak before you call it a voice. You can make this formal with models and posteriors, or you can keep a simpler habit. Write down before the night starts what you would consider convincing for each kind of effect, and then hold yourself to your own terms. Subtle signals often live at the edges of instrumentation, so you treat edges with respect. Flat fields taken at the start of the night can age as dust motes crawl, or as the optical path breathes with temperature. You can be fooled into seeing a jet that is just a moving grain on the detector window casting a small shadow. You fix this by building a master flat from the same night, by dithering the field slightly so the sky moves across the sensor but the comet stays centered in your measurements, and by inspecting star residuals in difference images to ensure their symmetry. Every fix that makes a subtle result more boring is a step toward truth. Change point detection is a practical tool for the quiet surprises. Instead of asking whether an entire light curve fits one line well, you ask where the best split would be if the behavior genuinely changed midstream. Algorithms that search for a minimum in the residual error with a penalty for complexity will find the place, if it exists, where a new slope begins or a new variance appears. A small, sudden drop in scatter after guiding improved does not count as comet physics. A small, sudden rise in brightness that persists through a guiding change does. Mark the times, note what else changed, and you learn to separate your hands from the sky's hands. Blind analysis is an honest friend when you're listening for whispers. Decide on the pipeline, the apertures, the clipping rules, the cadence before you look at the outcome for the target. Test everything on fake data into which you have injected signals of known size and timescale. Small brightenings, tiny colour drifts, a faint periodicity, so you learn how often your methods falsely detect and how sensitive they are to what you care about. Only then unblind the real sequence. If the subtle signal appears where your tool would have found it in the injections, you allow yourself a breath. This ritual is slower up front and calmer at the end. Correlation is not persuasion unless it respects causation. Thin cloud will brighten the sky in both filters and produce an artificial colour change if extinction differs by wavelength. Air mass will dim the field as the object lowers and can masquerade as a long trend. Moonlight alters polarization in ways that look like grain evolution. You correct these with reference stars, with extinction curves measured the same night, with models of sky brightness versus lunar angle. Then if a residual remains, it has earned the right to be interesting. The good habit is to assume you're wrong and then let the data talk you out of that assumption step by step. Cross-checks turn a near signal into a near fact. If a faint gas line seems to rise, another line from the same parent should rise too, even if more quietly. If the colour index shifts, the polarised fraction often shifts in a related way if the grain population is changing. If the innermost coma brightens, a slight increase in non-gravitational acceleration may follow days later as sustained jets thicken. If one telescope reports a nuance, another on a different night and a different instrument should be able to sketch the same nuance at a compatible level. Whispers grow bolder when the choir is wider. Human perception has its own biases, and subtle analysis is where they matter most. We are pattern-hungry and comfort-seeking. We prefer symmetry and closure. To keep those tastes from writing over the sky, you keep an audit trail. Every plot labelled, every parameter fixed or justified, every discarded frame explained. You hand the data, with descriptions, to a colleague who did not watch the night unfold and ask them to reproduce your result. If they can, the signal has survived the most ordinary form of skepticism, the healthy kind that simply asks whether another careful person arrives at the same place by the same road. Some surprises are the absence of what you expected. A predicted surge at small phase angle does not arrive. A line that should be visible at perihelion refuses to show. The coma remains round through a rotation when a lopsided jet seemed inevitable. These are not failures, they are constraints. No surge above this level cuts down scenarios about grain sizes. No line at this sensitivity limits volatile fractions. No asymmetry to this scale bounds jet strength or tells you the spin pole is pointing at you. Silence, tabulated, becomes quiet architecture for the later chapters where louder events happen. Confidence benefits from layers rather than height. One enormous plot with tiny error bars can be more fragile than 5 modest plots that lean on each other. A small periodicity, a small colour drift, a small asymmetry in the inner profile, and a small uptick in alpha, all aligned in time, amount to more than any one of them would. The point is not to chase significance until it snaps, but to collect mutually supportive hints until the only reasonable reading is that something genuine, if gentle, has been happening. The tone you keep matters. Subtlety rewards plain language. We detect a 0.06 magnitude brightening over 90 minutes, significant at the 3 sigma level, after correcting for air mass and thin cloud consistent across 3 reference stars and 2 filters. This is not shy, it is clear. Then you add a Lomskargel periodogram shows a peak near 5.1 hours, false alarm probability 2%, but this requires confirmation. This is not hedging. It is alignment with the truth as it stands. Say what is known, what is likely, what is merely attractive, and keep them separate. Instruments can be tuned for quiet listening. Faster readout with slightly higher read noise may be worse for bright work, but better for capturing fast flicker. A larger aperture for photometry increases noise from skewy but stabilizes against seeing changes for extended comae. Narrowband filters that throw away most light become heroes when you want a clean gas signal without dust confusion. Small telescopes, plentiful and nimble, become powerful when coordinated to fill in gaps that big observatories cannot schedule. Quiet science is democratic that way. It values steadiness over size. Finally, there is the practical mercy of stopping rules. You could watch forever and always find a small pattern that did not appear last hour. Decide in advance when enough for tonight arrives. A certain number of frames, a certain coverage of rotational phase, a certain precision on colour or polarization. Stopping is not surrender. It is what lets you sleep and return with the judgment to tell a real whisper from a remembered one. Subtle work is not about proving you can hear better than anyone else. It is about arranging the room so that if the comet says something soft and true, the microphones, the notebooks, and the eyes all agree at once that they heard the same thing, and they can show how they know it in detail without raising their voices. In most pictures, the dust tail streams away from the sun, a soft fan that curves gently like smoke in a breeze, while the ion tail draws a straighter, narrower lance in the exact anti-solar direction, yet sometimes a spike seems to stand on the sunward side as if the comet were dragging its hair forward into the wind. This is not a comet breaking the rules. It is geometry reminding us that rules, when seen from certain angles, can look inside out. The dust grains that leave the nucleus feel 2 main pulls. The sun's gravity tugging inward, and radiation pressure pushing outward. The balance between them is summarized by a number astronomers called beta, the ratio of radiation pressure to gravity. Tiny bright grains have large beta and get shoved hard. Large dark grains have small beta and barely notice the push. Immediately after release, grains start their own orbits around the Sun, not following the nucleus anymore but tracing slightly different paths depending on beta and launch speed. What we call the dust tail is the overlay of millions of these independent arcs projected into our line of sight, and projection is where the wrong way can appear. Two families of curves help turn the mess into meaning: synchrones and syndines. A synchrone connects particles released at the same time but with different beta. A syndine connects particles with the same beta released at different times. In a perfectly steady outflow, the dust-tail pattern is a woven fabric of these curves. The classic Finson-Probstein model computes how each grain's solar orbit evolves and then projects the result onto the sky from Earth's moving vantage point. The familiar broad anti-solar fan is dominated by small high beta grains released recently. These flee outward and arc away. The fainter, straighter skein along the orbital path, sometimes called the dust trail, is made of larger, low beta grains released long ago. These hug the comet's trajectory with stubborn inertia. When Earth crosses the plane of the comet's orbit, our view flattens the three-dimensional sheet of dust into a line of sight so that distant, slow grains behind the nucleus line up with nearer grains in front of it. The projection compresses depth into brightness and, for a few days, can make a sharp anti-tail appear on the sunward side. Nothing truly points toward the sun. We are simply looking edge-on through a sheet that happens to be tilted just right, and the line of maximum column density lands in front of the nucleus from our perspective. Recognizing an anti-tail starts with timing. These features often pop up when the Earth-Comet-Sun geometry places us near the comet's orbital plane, a condition you can calculate from the inclination and node of the orbit and the dates when Earth crosses that plane. Observers watch the phase angle, the Sun-Comet-Earth angle, because forward scattering by dust can brighten whatever structure sits near the anti-solar line, but the sunward spike typically demands the plane-crossing alignment. At such times, the tail system can look three-armed: a broad dust fan anti-solar, a thin blue ion tail exactly anti-solar, but offset by solar wind direction, and a narrow sunward spike that is really the near/far edge of the dust sheet. As days pass, the spike migrates and fades as our sightline moves off the sheet. Because the anti-tail is dominated by larger, older particles that have had time to spread along the orbital arc, it can look straighter and more needle-like than the fresh dust fan. And its brightness profile often falls more slowly with distance because the path length through the sheet stays high over many arc seconds. Ion tails never do this trick. Ions are born in the coma when ultraviolet sunlight strips electrons from molecules. The charged gas then couples to the interplanetary magnetic field and is carried anti-solar, often at tens of kilometers per second relative to the comet. The result is a narrow, often kinked or braided bluish tail that points almost exactly away from the sun, regardless of the comet's motion. That rigidity explains striking disconnection events when a passing magnetic sector boundary in the solar wind snaps the ion tail off. The tail appears to detach and rebuild, a space weather signature riding on comet physics. If a sodium tail is present, a rare delicate line emission from neutral sodium atoms, it too generally points anti-solar because radiation pressure pushes the resonantly scattering atoms outward. It can be very straight and narrow, but not sunward. So when you see a bright spear apparently toward the sun, dust and projection are the culprits, not ions rewriting their rules. Curvature encodes grain size. In a stacked image aligned on the stars, the dust fan bends gently. Modelers overplot syndines labelled by beta to estimate the mix of particle sizes. Higher curvature close to the nucleus indicates dominance of small grains recently launched. A stiff, shallow curvature or array aligned close to the orbit implies large grains released many days or weeks earlier. If you shift to an alignment on the comet's motion, The starfield smears and the inner dust structure sharpens. With azimuthal median subtraction, removing the smooth component of the coma, you can enhance faint jets and rays, revealing spokes that rotate with the nucleus and feed the tail. These spokes often seed synchrones. A burst of dust at a particular rotation phase creates a set of grains that, after a day or two, appear as a thin stria in the tail at the location predicted for that ejection time. Observers can sometimes count multiple synchrones like tree rings, each a timestamp of activity. Kinematics clarify the wrong way illusion further. Imagine the comet moving along its orbit with velocity v sub c. A grain released with negligible launch speed relative to the nucleus, but with beta greater than 0, immediately adopts a heliocentric orbit with specific angular momentum and energy slightly different from the comet's. For beta close to 0, large grains, the new orbit nearly matches the comet's, so the grain lingers near the path, gradually shearing into a trail both ahead of and behind the nucleus. For beta around a few percent fine dust, the effective solar gravity is reduced, the orbit's curvature weakens, and the grain drifts anti-solar, carving the broad fan. When Earth's line of sight is tangent to the grain sheet, the local density and path length spike, and radiative transfer turns that tangency into a bright ridge. Whether that ridge lies sunward or anti-sunward on your detector depends entirely on the projection at that date, hence the anti-tail. The equations are simple in principle. Integrate grain trajectories with mu arrow, left parenthesis 1 minus beta right parenthesis mu, then rotate into the observer's frame and project. The poetry is in how those trajectories stack in the sky to fool your intuition. Photometry across the tail system quantifies the story. Measure surface brightness along cuts through the anti-solar fan, along the orbital turtle trail, and along the sunward spike if present. Plot brightness versus projected distance and fit power laws. Different slopes portray different grain populations and emission histories. Colour measurements, say a red filter minus a blue filter, can distinguish the spike's grain sizes from the fans. Larger grains tend to produce redder colours because of their composition and scattering behaviour. Polarimetry adds another lever. The degree of linear polarisation often peaks at phase angles around 90 degrees, and deviations from the typical comet polarisation curve can signal unusual aggregate structure or size distributions, helping to confirm that the sunward feature is a sheet of large grains rather than an instrumental artifact. Time adds depth. Over several nights, the anti-tail can swing from one side to the other as Earth crosses the plane, turning a sunward spike into a symmetric edge brightening and then into part of the anti-solar fan. Synchrons drift outward by predictable amounts as dust ages, so their motion between nights can be used to back out the original ejection times, even if the nucleus was too faint for rotational light curves. If an outburst occurred, an impulsive increase in dust production, the tail will record it as a new, crisp synchrone that can be timed by its location relative to the nucleus, independent of any brightness spike in the inner coma. In very active comets, overlapping synchrons can create a violin string texture across the fan. In a calmer visitor, the fan stays smooth, and the only sharp feature is the anti-tail near plane crossing. There are pitfalls that make wrong-way mirages. Scattered light from a nearby bright star can paint a wedge that looks like a sunward spike. Checking multiple dither positions and subtracting a model PSF reveals the trick. Imperfect flat fielding can leave residual gradients that masquerade as a thin ray. Rotating the field or comparing to frames taken with the comet shifted on the detector defeats this. Thin cirrus can imprint streaks that align with wind direction, not comet geometry. Comparing to reference stars and checking weather logs saves you from claiming cloud as comet. A sodium or ion tail projected nearly along the anti-solar line can be mistaken for dust if only broadband images are used. Adding narrowband filters or spectra separates line emission from continuum and sorts identities cleanly. For interstellar comets, the tail physics is the same, but the tempos can differ. CO-driven activity far from the Sun can produce finer grains earlier, making a fan visible at larger heliocentric distances. If the nucleus is small and the gas drag modest, the dust distribution may skew toward larger grains, emphasizing the trail and anti-tail around plane-crossing dates. The absence or weakness of gas lines might mean that broadband images are the main tool, putting extra weight on geometry and projection to read the structures. The reward is that the tail becomes a mechanical seismograph for the surface. The sizes of grains the gas can lift, the speeds they leave with, and the times they were emitted all drop out of careful fits to curvature and brightness, telling you about cohesion, vent strength and rotational pacing without ever seeing the nucleus directly. Explaining the apparent wrong way to any age can be done with a flashlight and flour. Shine the light to stand in for the sun, toss a pinch of flour to stand in for dust, blow gently to stand in for radiation pressure. Small flour flies away fast. Pebbles on the table don't move. Now tilt a clear sheet with flour on it and look along the edge. The flour sheet seems to pile into a bright line where your view is edge-on, and depending on where you stand, that line will appear on the near side or far side of the source. Nothing reversed the direction of the push. Your perspective changed the way the sheet looked. The comet's anti-tail is that edge-on line in space, momentarily bright because millions of large, slow grains happen to stack along your sightline. Seen this way, a tail that points the wrong way is not an exception, but an extra diagnostic, a free tomography slice through the dust architecture. It tells you that Earth is skimming the comet's orbital plane. It singles out the population of older, larger grains. It timestamps past activity. It provides independent checks on the beta distribution and on ejection speeds. And it lets small telescopes do geometry that rivals sophisticated models simply by watching how the spike appears, sharpens, and slides over a handful of nights. The sky is generous like this. Even its illusions carry measurements, and a spike that seems to defy sunlight is, on closer reading, sunlight's most faithful servant, pushing, projecting, and revealing the layered paths of dust in a way that makes our intuition pause just long enough to learn. Light from a comet is a mixture of two stories: sunlight reflected by dust and sunlight re-emitted by gas after atoms and molecules have been nudged into special states. And spectroscopy is how we separate those voices so they stop talking over one another. A spectrograph spreads light into wavelength, blue to red, ultraviolet to infrared, using a grating or prism, then records that rainbow as counts per pixel. The horizontal axis becomes wavelength. The vertical axis becomes intensity. With enough resolution, you see narrow features sitting on a sloped background. The slope is the continuum from dust shaped by grain size and composition. The narrow features are emission bands from gas species fluorescing under solar radiation, plus a handful of forbidden atomic lines set aglow by photochemistry. Even a modest instrument can show the green C2 swan bands in the visible, the violet CN band near 388 nanometers, the broader C3 in the blue, and, in the near UV, OH lines that trace the breakdown of water. Higher resolution and sensitivity add the sodium D lines around 589 nanometers, and the forbidden oxygen lines at 557.7, 630.0, and 636.4 nanometers, which are especially useful because they tie directly to water photodissociation through well-understood pathways. Farther into the infrared, spectrometers pick up vibrations and rotations of H2O, CO2, CO, CH3OH, HCN, and other molecules, while in the thermal infrared the dust itself emits, letting you weigh grain temperatures and mineralogy. Radio receivers catch pure rotation lines from molecules like HCN or CH3OH, whose Doppler profiles reveal expansion speeds in the coma. Together, these colours we cannot see give you chemistry, physics, and motion at once. Getting to a trustworthy spectrum is a game of careful subtractions and ratios. Before the science frames, you record arc lamps, neon, argon or thorium-argon, so every pixel maps to a precise wavelength. You observe a spectrophotometric standard star to turn counts into physical flux. You take flats to remove pixel-to-pixel sensitivity changes and fringing in the red. You measure the night's extinction with air mass, so blue light's extra loss is corrected. You divide by a solar analog star if you want the dust's reflectance spectrum, the comet's continuum normalized to the sun's colour, so you're reading the dust's personality, not the star that lights it. You subtract the sky carefully, because airglow lines, especially oxygen, and scattered moonlight can masquerade as comet signals if the slit crosses a crowded field. On bright comets, you can nod along the slit, A, B, B, A, to capture sky and coma alternately. On faint ones, you offset to a clean patch of sky between exposures. Finally, you correct observation times to the barycentric frame, and, for gas fluorescence, note the heliocentricidal velocity. Because the swings effect, Doppler shifts between the solar Fraunhofer lines and the comet's molecules, modulates pumping rates and therefore line strengths. Once the spectrum is calibrated, the dust continuum becomes a diagnostic rather than a nuisance. If you divide by a solar analog and smooth, you obtain a reflectance slope, often expressed as percent per 100 nanometers. A red slope indicates larger or more organic rich grains. A neutral or slightly blue slope hints at finer grains or different composition. Changes in slope with time, phase angle, or aperture size tell you whether the inner coma has fresher material than the outer halo, whether forward scattering is boosting big, transparent grains, and whether grain evolution is underway as the comet warms. In the thermal infrared, a rising continuum with a silicate emission feature near 10 micrometers reveals the grain temperature distribution and the presence of amorphous or crystalline silicates. The shape and contrast of that band, together with a secondary approximately 20 micrometers feature, constrain olivine/pyroxene mix and the fraction of annealed crystalline material, which in turn reflects how much high-temperature processing the dust experienced before it was built into the nucleus. Gas features are read with simple integrals and careful models. You measure an emission band's area above the continuum and convert it to a band flux, with a fluorescence efficiency, a G factor, appropriate to the heliocentric distance and velocity. You infer the column density of the parent or daughter species in your slit. A Hazer model, an idealized picture of parent molecules decaying into daughters as they stream away, turns that column density into a production rate in molecules per second. Do this for CN, C2, C3, NH, OH, and you build a chemical ledger through the night and across nights. Which species rise faster with decreasing heliocentric distance, which lag, which peak, and then fade. Ratios like C2 over Cn or Cn over OH, and absolute OH as a proxy for water, sketch the comet's volatile inventory. If the object is interstellar, unusual ratios become especially valuable because they say this kitchen stocks different ingredients without your ever touching the nucleus. In the near IR, direct H2O, CO2, and CO lines provide cleaner budgets, and the relative strengths of hot and cold bands give a rotational temperature, often 50 to 120 Kelvin in the inner coma, that reflects how collisions and radiation balance in the gas. Line profiles add kinematics to chemistry. At moderate spectral resolution, cometary emission bands are broadened not by thermal motion alone, but by the bulk expansion of the coma. Typical full widths correspond to outflow speeds of 0.5 to 1.0 km per second near 1 astronomical unit, trending lower farther out. If you orient the slit sunward anti-sunward, you sometimes see subtle centroid shifts across the nucleus. Blue shifted sunward, where gas flows toward you, red shifted tailward, where it recedes, evidence of anisotropic outgassing and jets. Sodium D lines, when present, can be strikingly narrow and sometimes show a separate, faster component if a sodium tail form. Forbidden oxygen lines provide an independent handle on water. The intensity ratio between 557.7 nanometers and the red doublet near 630.0/636.4 nanometers depends on the photochemical pathway and can be modelled to check whether water or CO2 is the dominant parent in that region. In high-resolution spectra, isotopologues occasionally separate just enough, 13CN beside 12CN, or minor shifts in NH2 sequences, that you can estimate 12C over 13C or 14N over 15N, and in the infrared, water's multiple lines can, with heroic signal, constrain D over H. Each isotopic ratio is a small flag planted in the landscape of formation temperatures and disk histories. Spatial information turns a single spectrum into a map. A long slit crossing the nucleus records brightness as a function of wavelength and distance from the centre. Extracting rows yields a series of spectra at different Comte-centric distances. Gas bands typically peak centrally and fall with a scale length set by photodissociation lifetimes and outflow speeds. Dust continuum falls differently, so the gas-to-dust ratio changes with radius. If a jet is active, one side of the slit can show enhanced bands relative to the other, and the excess will rotate with the nucleus over hours, offering a tomographic look at active sources. Integral field spectrographs go further, delivering a data cube, 2 spatial dimensions plus wavelength, so you can plot, for example, a CN map and an OH map over the same field and see whether they trace the same vents. Even small telescopes can emulate this by sliding the slit across the coma in steps and mosaicing the extractions. Telluric and instrumental effects need disciplined handling because subtle errors masquerade as physics. Water vapour in Earth's atmosphere imprints deep bands in the near IR. You divide by a hot, nearly featureless star at similar air mass to remove them, then restore the star's black body shape. In the red, CCDS can show fringing, sinusoidal sensitivity ripples from internal interference that flats partly remove, but residuals can imitate broad, low-contrast bands if you're unlucky. Dithering and careful flat construction reduce this. Order overlap in a shell spectra must be separated cleanly to avoid cross-contamination. These spectrographs' scattered light can fill in between lines, flattening contrast and undercutting abundances unless the instrument profile is deconvolved. And because many fluorescence bands sit near or on top of solar Fraunhofer lines, small calibration errors in wavelength or in Doppler correction can change measured fluxes. The swings effect is real physics, but it must not be confused with a calibration wobble. With clean spectra, the dust's continuum becomes more than a slope. It can show subtle bumps from broad organic features, a gentle change in curvature with phase angle, phase reddening, and, in polarized spectroscopy, wavelength-dependent polarization that flags aggregate structure. In the mid-IR, fitting the 10 micrometer silicate band with mixtures of amorphous olivine/pyroxene and crystalline forsterite/enstatite plus a distribution of grain sizes lets you estimate the crystalline fraction. Finding a significant crystalline component implies high temperature annealing somewhere in the parent system, followed by outward transport, a clue to disk mixing efficiency. Conversely, a very featureless dark continuum hints at heavily processed, carbon-rich grains that mute silicate signatures, aligning with a history of radiation chemistry in deep cold. Ultraviolet spectra, when available from space-based platforms, complete the picture by isolating OH, CS and CO bands in cleaner windows, free from the forest of visible bands. OH in the UV is the most direct ground-accessible water proxy, but space UV avoids atmospheric absorption entirely and can reach weaker transitions that help pin down production rates under marginal conditions. In the radio, millimeter arrays can spatially resolve molecules like HCN across the inner coma, measure line wings to map outflow acceleration, and even detect hyperfine structure for optical depth diagnostics. These domains are not luxuries. They cross-check one another so that a high CN/OH ratio seen in the visible is supported by HCN/H2O in the radio, or challenged by CO2 dominance in the IR. For a visitor from beyond, spectral accents are where the excitement concentrates. A CO-rich H2O-poor mix at large heliocentric distance would suggest ices near the surface that formed at very low temperatures consistent with a parent disk's far outskirts. An unusual C2 over Cn ratio could signal different carbon chemistry, perhaps fewer hydrocarbons or altered photolysis histories in the parent system. A sodium tail without strong dust continuum would be odd and informative, pointing to surface mineralogy and liberation processes. If, by great fortune, isotopic ratios diverged from the tight clusters seen in most solar system comets, even modestly, the case for genuinely different protoplanetary conditions would be strong. In all of these, restraint is key. Detection limits and swings effect modulations must be folded into any claim, and night-to-night repeats should be sought before interpretations harden. Practical observing choices steer outcomes. A low-resolution GRISM, R approximately 300 to 1000, maximizes sensitivity to faint continua and broad bands, ideal for first detections and color slopes. A medium-resolution spectrograph, R approximately 2000 to 10,000, resolves the brighter bands well enough to fit baselines, separate and blended species, and measure expansion velocities. And a shell, R approximately 20,000 to 100,000, unlocks kinematics and isotopic structure, but demands more signal and stricter calibration. Pore slits improve spectral resolution, but lose light and are sensitive to guiding. Wide slits secure flux but blur spatial information and mix nucleus and coma. Many teams compromise, a wider slit for absolute fluxes and a narrower one for line profiles, bracketed by standards to tie the pieces together. Across all setups, good logs matter. Air mass, seeing, slit position angle, offset from the brightness peak, sky transparency notes, because later, when a small ratio shift matters, you will want to know whether the slit crossed a jet or missed it by a few arc seconds. From these spectra, you build a small set of curves that summarize a night's invisible colors. Reflectance slope versus time, production rates Q of Cn, Q of C2, Q of OH versus heliocentric distance. Line width versus time, as outgassing speeds change. Simple gas-to-dust proxies like Q of OH over AFRHO, showing whether dust or gas led the activity. You annotate them with geometry, phase angle, heliocentric distance, geocentric distance, and the comet's heliocentric radial velocity for the swings effect. If the curves cohere, gas rising as the comet approaches the Sun, OH tracking water, C2 and Cn maintaining a steady ratio, unless an outburst injects fresh chemistry, you begin to trust your read. If they contradict, you look harder. Perhaps our icy grains extended the OH distribution beyond the slit. Perhaps a jet rotated out of the aperture mid-sequence. Perhaps moonlight lifted the continuum and depressed apparent band strengths until corrected. Each tension is either a clue or a calibration. Both are useful. In the end, spectra turn a pale, fuzzy blob into a ledger of processes. The continuum slope says how dust is built and how it changes in sunlight. The band intensities say which ices are driving the coma and how quickly they're being fed. The line shapes say how fast gas escapes and in which directions. The ratios say something about a birthplace's cold and warm spells, about mixing in a parent disk, about exposure to radiation over long drifts between stars. None of this is visible to the eye at the eyepiece. It becomes visible when you let the light run through a grating, subtract Earth's sky, divide by a standard, and accept that the most revealing colours are the ones our eyes never evolved to see, the ones that turn a whispering visitor into a set of clear, testable sentences written in wavelength and time. No single instrument hears everything. The sky is a choir, and each voice carries a different harmony. The small, fast survey telescopes keep the beat. They sweep great arcs of darkness every clear night, with wide cameras and short exposures looking for motion and change. Their cadence is relentless. Image, shift, repeat, compare to last night and last week and last month. Software subtracts yesterday from today, and any new point that walks between frames earns a flag. These systems, scanning for asteroids that might one day matter to us, also net visitors that matter to curiosity. They give coordinates, rates on the sky, a brightness estimate, and a timestamp accurate enough that anyone, anywhere can point and expect to see what was seen before. This is the opening note, the metronome that sets everyone else in motion. Around that beat, narrow-field instruments sing detail. Medium and large optical telescopes take deeper exposures that would be too slow for surveys. They trade area for depth, field for precision, and begin to separate coma from tail, jet from haze, nucleus from grain glow. They flip in filters, blue, red, narrowband for gas species, and build a layered picture that is richer than a single white light view. One team might sit on broadband for hours to gather a clean light curve while another cycles CN and C2 to follow gas, and a third uses a polarizer to measure how dust grains twist the light. These are not redundant, they're complementary. When you lay their plots on top of each other and time align them, peaks in one explain plateaus in another, and the night's mixed signals become a readable sentence. Space-based observatories contribute quiet colours that the atmosphere swallows. A satellite with ultraviolet sensitivity maps OH without fighting airglow, and watches CO bands without ozone in the way. An infrared space telescope measures water, carbon dioxide and carbon monoxide directly, sees the warmth of dust grains rather than just their reflected sunlight, and extracts mineral fingerprints from silicate features that the ground only hints at. In the far infrared, a faint thermal tail that the eye never sees turns into a measurement of grain size distributions and temperatures. Space does not replace ground, it anchors it, providing absolute scales where the air wobbles and filling spectral windows that Earth keeps shut. Radio dishes take the slow, steady lines that optical spectrographs cannot. Millimeter receivers tune to rotational transitions of HCN, H2, CO, CH3OH, and other molecules, and by reading the line widths and shapes they recover out flow speeds without guessing. Arrays combine dishes across kilometers to resolve structure in the inner coma that a single mirror would blur. The hyperfine splitting in a molecule's radio line can reveal optical depth. Asymmetries between sunward and tailward pointing show jets even when the brightness looks round. Radar, when geometry and size permit, adds a different kind of echo, direct range and Doppler information on a nucleus. But for most distant visitors, the radar note is too faint, so the radio's molecular whisper remains the main long-wavelength voice. Photometry from small telescopes knits time zones together. A single observatory loses the sky when morning arrives or weather turns, but a ring of modest apertures, amateurs with scientific cameras, university instruments, national facilities, can hand off the target at dawn like a baton in a relay. Europe to the Americas to the Pacific to Asia and back again. The light curve becomes continuous, and rotation periods that would alias in an 8-hour stretch now settle into clean values. This is one of the most democratic strengths in astronomy. Precision does not always require a giant mirror. It requires persistence, calibration, and many eyes willing to share their nights. Polarimetry, often overlooked, adds grain physics that no colour can. By measuring how much the light is polarised at different angles from the sun, and how that polarisation changes with wavelength, you infer whether the coma's dust behaves like fluffy aggregates of tiny monomers or compact chips of rock and glass. A network measuring polarisation across phase angles that one sight cannot reach, some at small phase angles near dawn or dusk, others at larger ones late at night. draws the full polarization curve for the visitor and plugs a gap that would otherwise be filled by assumptions. It is not flashy, but it is decisive when composition and texture blur together in spectra. Geometry demands a globe. The comet's position against the stars changes with Earth's rotation and orbit, and the phase angle, the Sun-Comet-Earth triangle, moves the scattering into or out of favourable regimes. A sight in the south can see the visitor high and sharp when a northern sight must look through thick air near the horizon. An equatorial observatory can ride the object across the meridian for hours, escaping the latitude limits that frustrate the poles. A high, dry desert gives low water vapour for infrared measurements, while a northern winter sight trades humidity for long nights and stable seeing. When teams share not only data but plans, we will take spectra of 5,000 from 1 to 4. Can someone cover red polarimetry after 4? The whole globe becomes one instrument with pieces arranged to match the sky's constraints. Scheduling is music too. Survey systems publish when they will sweep a region. Follow-up facilities book slots around those times. Space telescopes require proposals months in advance, but a well-timed target of opportunity trigger can redirect them when something unexpected happens. The best campaigns mix rigid and flexible, a backbone of regular measurements to catch slow evolution, plus slots reserved for outbursts or geometry windows, like when Earth crosses the comet's orbital plane and an anti-tail may appear. This blend of structure and responsiveness is how you listen for both melody and improvisation. Calibration is the shared language that lets these voices harmonize. Everyone ties their magnitudes to the same standard star catalogues, reports the same filter systems, uses comparable apertures, or clearly states their equivalent radii. Spectroscopists note the slit width and position angle, and whether the slit crossed the brightness peak or sat offset to avoid saturation. Radio teams report beam sizes and main beam efficiencies. All include air mass, seeing, and weather notes because a thin cloud over one site is a false slope in someone else's comparison. With this metadata, you can put a point from a backyard telescope next to a point from a national facility and trust that the difference between them is sky, not bookkeeping. Data paths must be short. A central clearinghouse for astrometry updates ephemerides in near real time, so nobody is pointing at yesterday's sky. A shared repository for reduced photometry, spectra and polarization lets people overlay curves within hours, not weeks. Versioning matters. When a reduction pipeline improves, the new curves do not silently replace the old. They live alongside with notes about what changed. In the middle of a campaign, this is not paperwork. It is how you avoid chasing artifacts that evaporate when a fringe pattern is removed or a flat field is rebuilt from better twilight frames. Citizen science is not an afterthought. Thousands of observers with modest gear can measure the comet's brightness in standard filters and upload results that, when carefully filtered and averaged, provide nightly coverage that professional facilities cannot match. Their images, aligned and stacked, reveal jets and synchrones that inspire targeted spectroscopy from large telescopes. Their time series, even if noisy individually, fuse into precise curves when hundreds of points are combined. Their geography fills holes. A clear night in a small town can bridge a week-long storm at a major observatory. Inclusion is not charity. It is strategy. Different wavelengths bring different clocks. Ultraviolet shows parents and daughters in the earliest minutes after release. Visible bands mix gas and dust on hour-long timescales. Near-infrared traces ices and hot bands that respond as vents swing into sunlight. Thermal infrared reacts to grain temperature, lagging behind sudden changes as dust warms. Radio transitions are sensitive to density and excitation set by collisions and sunlight integrating over the inner coma's last few hours. If the team watches across these clocks at once, a surge in one domain that precedes a rise in another becomes causal instead of coincidental, and you can say which parts of the system lead and which follow. Space weather folds into whole sky listening. Solar wind monitors upstream of Earth report density, speed and magnetic field polarity. When a sector boundary is due, teams expect an ion tail disconnection and plan imaging to catch it. If a coronal mass ejection is forecast, observers brace for aurora that complicates sky subtraction at high latitudes and for tail kinks that tell more about the heliosphere than the nucleus. None of this is noise if you're ready. It is an extra instrument playing through the comet. And by correlating tail behaviour with solar wind data, you learn how the visitor's plasma environment breathes. Analysis unites the choir into a score. A synthesis team gathers the photometry, spectra, polarization, and radio lines and fits a time-dependent coma model. Gas production rates that drive dust ejection, dust-sized distributions that evolve under radiation pressure, jets tied to a rotating shape and non-gravitational forces nudging the orbit. They run forward models to predict light curves and tail shapes and compare to the actual images. Where the model fails, physics is missing. Perhaps icy grains extending water production, perhaps clathrate release adding CO late, perhaps porosity changing as dust aggregates compact in sunlight. The model is not the goal. The mismatch is the lesson that tells you which knob in nature was actually turned. Redundancy is a safety net. Two teams observe the same line with different spectrographs and arrive at the same production rate within errors. Two photometry sets taken hours apart show the same slow 0.05 magnitude rise. A polarization measurement from one hemisphere agrees with another at the same phase angle a week later. Each agreement shrinks the space for accidental explanations. Each discrepancy triggers an audit, slip placement, sky subtraction, calibration stars, until either the data align or a real difference is found and explained by geometry or rotation. Transparency keeps the choir in tune. Negative results are posted. No CN detected down to a limit. No polarization above a few percent at a given phase angle. No periodicity detected within certain amplitudes. These nothings stop others from chasing phantoms and become constraints in the synthesis. Uncertainties are carried forward, not quietly dropped. When curves are combined, weights reflect those uncertainties so a noisy point whispers rather than shouts. This culture is not ornamental. It is the only way a global listening session avoids becoming a rumour mill. The whole sky is also time. Archival searches in past surveys sometimes find pre-discovery images where a faint point moved just as the later orbit predicts. These add weeks to the observational arc and sharpen ephemerides. Old spectra of similar comets provide priors for likely ratios. Old light curves offer templates for how long a spin period might persist. The new visitor is not alone, it fits into a lineage. By stacking today's hearing on yesterday's echoes, you tie one night's whisper to decades of recorded songs. When this works, the result looks simple, which is how you know you have understood something properly. A plot of water, carbon monoxide and dust proxies versus time shows smooth curves with a few honest bumps. A second plot of polarization versus phase angle sits on a familiar track. A third showing ion tail kinks lines up with solar wind shifts. A fourth with light curve period finds the same number from 3 continents. A map of the tail shows synchrones where the model puts them. The orbit prediction meets the sky to within a handful of arc seconds night after night. None of these required heroics alone. All of them required many modest acts done carefully and shared quickly. Listening with the whole sky, in the end, is not a slogan but a method. Distribute the watch, diversify the wavelengths, standardize the measures, synchronize the clocks, publish the nulls, invite the patient, and let the geometry and physics decide whose voice leads when. A visitor arrives, exhales, and continues on. We answer not with a single shout, but with a chord that holds long enough to capture what was said, and plain enough that later listeners can still hear it, even after the singer has long since slipped back into the dark. There is a moment in careful work when columns stop feeling like inventory and start feeling like melody, when a graph's line is no longer just ink, but a phrase that rises, holds, and resolves. You don't force that moment, you set the stage for it. First, numbers are cleaned, time stamps synced, outliers flagged by simple rules, noisy frames downweighted rather than erased, reference stars chosen for steadiness, extinction trends removed with low-order fits, backgrounds measured the same way every time, then the numbers are centered in their proper frames, barocentric times for periodicity, heliocentric distances for production rates, phase angle for scattering. Only after this housekeeping do the rows begin to align like notes on a staff. Patterns emerge at different tempos. Autocorrelation listens for echoes of a value in its own future, revealing whether a brightness today rhymes with brightness a rotation later. Cross-correlation asks whether gas rises first and dust follows, whether one filter's curve leads another by minutes or hours. A periodogram scans through trial frequencies and marks where variance is best explained by a repeating beat. It does not guarantee a song, but it points to keys worth trying. When a candidate period appears, you fold the light curve, wrapping time around that period, so scatter collapses into a shape. If the points arrange themselves into a smooth hill and valley, the ear of the eye hears it at once. If they don't, you adjust cadence, refine detrending, or accept that the rhythm is slower, faster, or less tidy than you hoped. Noise is not a villain. It's an instrument with its own timbre. White noise is the hiss between stations, uncorrelated from one moment to the next. Red noise drifts like weather, raising and lowering the baseline over hours. Scintillation flickers quickly. Transparency drifts slowly. Gaussian process models treat these as covariances rather than nuisances, letting you say, expect nearby points in time to share some gentleness, and then fit a signal atop that expectation. Kalman filters guide us a moving estimate frame by frame, incorporating each exposure as a new note in the same measure. These tools don't invent music, they remove the creak of the chair and the hum of the air conditioner so the soft instrument in the next room can be heard. Decomposition turns a crowd into a choir. Principal components analysis takes a matrix of many stars-like curves and learns the common modes, thin cloud, seeing, air mass, and subtracts them, leaving behind the part that belongs to the comet alone. Independent components analysis goes further when influences overlap, teasing apart sources whose shapes differ but whose times overlap. In spectra, non-negative matrix factorization splits the rainbow into familiar contributors, a dust continuum, a CN band family, a C2 family, a faint sodium pair. Each component becomes a track you can follow across time, so that when one rises, you know which physical lever was pulled. Model comparison gives discipline to enthusiasm. You try a constant model, nothing changed, a linear trend, slow breath, a sinusoid, rotation, or a piecewise constant, an outburst. For each you compute goodness of fit, yes, but also reward simplicity, an Occam penalty, using information criteria like AIC or BIC, or a full Bayesian evidence if you are patient. The best model is not the one with the lowest residuals alone. It is the one that explains the structure without memorizing the noise. Posterior predictive checks then ask a blunt question. If this model were true, would it generate data that look like tonight's? You simulate fake nights from the fitted model, and if those fakes lack the quirks your real curve shows, the model is missing an instrument and needs another line in its score. Residuals are where the new music hides. After you subtract your chosen model, what remains should look like the noise you assumed. If it doesn't, if there is shape in the leftovers, you have found either a second instrument or a calibration sin. A weak harmonic at twice the main period suggests two bright regions on the rotating surface. A small step in the residuals at a certain time suggests a jet rotating into view or a change in slit placement. A gentle S-shape drifting through spectra or residuals hints at imperfect telluric removal or fringing. You do not scold the data for this. You thank them and revise the part list. Some structures are better heard in a different key. Wavelets let you look for periodicity that grows and fades like a motif appearing and then dissolving. They map power across time and frequency, showing a rotation signal that is strong near perihelion and faint before, or a transient oscillation after an outburst. Empirical mode decomposition lets the curve tell you its own intrinsic modes without imposing signs. Each mode can be examined for physical origin or left as a safe, agnostic summary of the shape you truly have. In all cases, you label what is interpretive and what is descriptive so that future you, or anyone, can retrace exactly where physics entered and statistics left off. Faint chemistry sings in ratios that steady the hand. For gas bands, you integrate carefully over windows that avoid skylines and divide by g-factors tuned to heliocentric distance and velocity, acknowledging the swings effect. Production rates plotted on a log scale versus distance from the sun should rise and fall with slopes that tell of drivers, water steepening near 3 astronomical units, CO holding farther out. If a ratio like C2 over Cn stays flat within errors, you call it typical with confidence. If it arcs upward or downward, you cross-check with nights you nearly threw out. Does the same arch appear when the moon was up, when the slip missed the core, when thin cloud passed? Only when the shape survives these unkind cuts do you upgrade curiosity to behaviour. Images have music too, azimuthal profiles, brightness as a function of angle around the nucleus, stacked across radii reveal repeating spokes. Rotate and difference pairs of frames separated by a quarter rotation, and subtle jets become mirror images of themselves. Fit synchrones and syndines to tail textures. The best fit launch times become percussive events in the past. A beat at -36 hours, another at -14. A quieter one at -7. Overlay these beats on the light curve. If they align with small rises, the percussion section and the melody are playing together. If not, you have learned that dust and gas are on different scores, as they often are. Visualization is a performance choice. A light curve with honest error bars and a thin, semi-transparent model line tells the truth more clearly than a thick, boastful fit. A corner plot of parameter posteriors shows trade-offs. A slightly shorter period demands a slightly larger amplitude to match the data, and together they still hum the same note. A waterfall plot of spectra, time on one axis, wavelength on the other, intensity as colour, turns a line's growth into a rising column and its fading into a cooling ember. A vector field over a coma image shows measured outflow directions, small arrows reminding you that gas has a direction, not just a count. These choices are not decoration. They are how you keep faith with the data. Uncertainty is not an apology. It is dynamics. Error bars are the volume markings, pianissimo where the measurement is precise, mezzo where the sky was unkind, forte where a burst forced short exposures and high scatter. Credible intervals around a period are the wobble you would hear if the rotation sped up or slowed down a little. Intervals around a production rate are the tremolo from thin cloud you could not entirely remove. When you report them, you are not weakening your song. You are teaching others how loudly to listen to each part. Sometimes numbers begin to sing literally. Sonification maps brightness to pitch, time to time, colour to timbre. A rising water production becomes a slow glissando. A periodicity becomes a repeating arpeggio. An outburst arrives as a plucked chord. This is not whimsy when done carefully. It can expose small regularities a quick glance misses and invite non-experts into the pattern, finding that graphs alone can make forbidding. But even without audible notes, the metaphor holds. A coherent pattern, once prepared, becomes as unmistakable as a tune you can hum. Integration is the chorus. You place gas production, dust proxy, polarization, tail curvature, period, and non-gravitational acceleration on a shared time axis. A rise in gas precedes a rise in dust by a lag that matches ejection and acceleration times for the measured grain sizes. Polarization dips when larger grains dominate, at the same time that the colour reddens. A small change in spin period, derived from phase drift, lands a day after sustained high gas output, consistent with torque. The orbit fit improves when you include those torques. and the prediction meets the sky a little more tightly the next night. Each agreement between lines is a harmony, the proof that different instruments are reading the same score. Discipline keeps the music from turning into self-fulfilling prophecy. You pre-register simple questions when you can. What period resolution you will accept, what amplitude marks a detection, what slope change you will call real. You blind names and nights so you don't cherry-pick the pretty curves. You split the data by telescope or by filter and ask whether both subsets keep the tune. You publish the code and the calibration frame so anyone can rerun the concert. The reward is not praise, it is the ability to believe your own melody tomorrow. When the numbers finally sing, they do not shout. They assemble, a period that returns in independent slices, a ratio that bends the same way in two instruments, a tail synchrone that lands where the model's line predicted, a gentle acceleration that the orbit solver needs whether or not you tell it why. The feeling is not triumph, but recognition, the way a theme you've been hearing faintly all along emerges cleanly when the rest of the orchestra drops away. What began as columns and arrays has turned, through calibration and restraint, into a phrase you can carry forward, a line that can be quoted in the next movement without strain, a part of the piece that will remain even when the visitor's light is gone from the screen and only the score of measured, well-behaved numbers remains. If a traveller from elsewhere carries a ledger, reading it teaches us as much about our own house as about theirs. Ratios we measure in the coma, water to carbon monoxide, carbon chains to CN, silicate crystallinity in the dust, do not only say their disk was like this, they also ask whether ours is ordinary. When a visitor's D/H in water sits high, low, or somewhere between familiar bands, it nudges the long argument over Earth's oceans. Were they delivered by comets, asteroids, or distilled out of the inner disk? If a stranger's water looks unlike the mix in our comets, that contrast suggests variety among planetary kitchens and implies that how to build oceans allows multiple recipes. If a visitor's dust shows a large crystalline fraction, it reaffirms that disks routinely move hot material outward across snow lines. If it shows very little crystallinity, it reminds us that efficient outward transport is not inevitable. Either way, our own crystalline silicates in comets stop looking like a special quirk and start looking like one end of a spectrum. The spectrum matters because it tells us how typical our protoplanetary weather was, how much stirring, how many shocks, how long high-temperature regions stayed hot. The way gas escapes from a nucleus, speeds, preferred directions, how quickly jets turn on with sunlight, feeds back to the physics of small bodies closer to home. We build models of porous ice dust mixtures, of vents with crusts that seal and crack with day-night cycles. When an interstellar comet fits the same simple laws that fit our long-period comets, outflow scaling roughly with the inverse square of heliocentric distance when water dominates, earlier activity when CO and CO2 run the show, it tells us that ice under starlight tends to behave similarly across disks. When it deviates, say a subdued response near the sun, or an unexpectedly vigorous outgassing far out, it suggests surface chemistry, grain size, or layering not common in our samples. That difference is not exotic for its own sake. It is an extra boundary condition in the equations we already use. The constants we thought were universal become distributions. The distributions describe a galaxy's worth of small body weather. Tail geometry and grain-sized distributions feed a subtler question. What did cohesion mean where we formed? Gas drag lifts grains against gravity and against interparticle forces. If a visitor consistently ejects larger grains at lower velocities than our comets do at similar distances, it hints at either stickier surfaces or different pore structures in the crust, which in turn hints at grain growth and sintering histories in its natal disk. The reverse, plentiful fine grains at large distance, points to fluffy aggregates that come apart easily, an index of gentle collision speeds in a colder, calmer nursery. These clues rebound onto us, our meteoritic textures, our comet dust samples from spacecraft, our polarization curves across familiar comets. Each can be reinterpreted in light of wider variation, either as one common outcome or as one of many stable arrangements. Light curves and their small periodicities read like heartbeats that tell us how small bodies spin, precess, and gradually change. If an interstellar nucleus shows a drift in period from gas torques comparable to drifts we see at home, the torque per mass relations we infer gain external validation. If it tumbles in non-principal axis rotation, we know that impacts and uneven vents produce the same wobbles in other systems that they do here. Our Yorp series, sunlights push slowly spinning small bodies up or down, gain a foothold beyond the sun if a long thin visitor shows telltale spin states. Every match is a vote for common mechanics. Every mismatch is an opportunity to ask which assumptions about strength, shape, or activity are too local. Isotopes are the small print at the bottom of the page that lawyers read and most of us skip. But in planetary science, they are where the contracts live. At 12C over at 13C in carbon-bearing gases, 14N over 15N in C, N, and NH. Oxygen fractionation seen indirectly through forbidden lines and OH. These tiny ratios are the clocks and thermometers of formation. If a visitor's ratios overlap the narrow bands we know from our comets and meteorites, it tells us that interstellar clouds and disks imprint similar isotopic accents broadly across the neighbourhood of the galaxy. It suggests common chemical starting points and processing. If they diverge even modestly, it makes our own inventory look less like a template and more like a case study. In both outcomes, home is clarified. Either our chemistry is typical and thus likely in other systems, or it sits along a recognisable gradient, and we learn where on that gradient the sun's disk lived. Volatile budgets at different distances trace heat and cold in two clocks, the clock of the visitor's parent disk and the clock of our observation geometry. CO-driven activity far from the sun implies abundant supervolatiles near the surface, which in turn implies mild heating during ejection and cruise. Water-dominated activity that switches on late hints at a more processed crust and deeper reservoirs. Our own comets carry both patterns, some CO warm, some water late. Seeing the same menu in a different proportion is evidence that the categories are not accidents of our observing bias, but staples of small body physics. If a visitor lacks familiar radicals or is unexpectedly rich in a rare one, it writes a footnote under our habit of using comets as probes of the early solar system. Your probe sample one pantry, the galaxy stocks others. Orbit and speed hold a sociology lesson. A hyperbolic excess velocity that aligns near the local standard of rest suggests a slow drift between stars, time enough for a small body to be sandblasted by cosmic rays, to grow a dark rind, to carry that patina as a badge. A markedly different direction or speed may connect to a moving group or a young association, where ejection is fresh and surfaces might be less processed. We learn that our solar system is not isolated in a tactical sense either. Dynamical lanes link systems. Our Oort cloud likely leaks and refreshes from such exchanges over eons. Home, then, is partly built from outsiders, and the outsiders we see are partly built from the same unfussy physics that make outsiders of us. Radiation chemistry's fingerprints, red and dust, suppressed silicate features, complex organics, loop back to a question often asked softly: how common are the ingredients that make prebiotic chemistry easy? If a visitor carries abundant complex organics, we are invited to think of organic coatings on dust as the default condition in cold zones of disks. If it carries less than we expect, it reminds us that UV fields and cosmic ray histories sculpt inventories significantly. Our prejudice that space makes organics everywhere gets calibrated. We do not need to invoke biology to let this matter. It matters because the ease with which disks build complex carbon sets the floor for the chemical richness planets inherit. Knowing where we sit on that floor is one way of saying whether our kitchen was well stocked before the stove ever lit. Even the ways we fail to detect things at the limit, no CN above a threshold, no sodium tail down to a sensitivity, no polarization beyond a few percent at certain phase angles, say something about home. They tune our expectations for future visitors and push us to check whether our own comets are really quiet in those same corners, or whether our instruments and habits simply made them look that way. When a visitor forces us to rebuild a flat field, to account for the swings effect more carefully, to coordinate small telescopes across time zones, it improves our vision for everything else. The lessons about us are procedural as well as physical. How to move from anecdotes to distributions, from pride in a favourite comet to humility in a population. On a wider scale, each traveller widens the error bars we place on claims about how disks mix and migrate. Our models of giant planet migration, the NICE model and cousins, depend on how easily small bodies can be thrown outward or inward. A visitor with signs of strong inner disk processing in its outer disk ices argues that outward transport was vigorous in its home, strengthening the case that vigorous transport may be common. A visitor with very primitive signatures and little processed dust argues that quiet disks exist too, cooling our urge to universalize any one migration history. Home becomes, in this reading, not a rulebook, but one point in a family portrait. We can see who we resemble and who we don't, and neither resemblance nor difference is a compliment or an insult. Both are information. There is also the human home that gets measured. The way a small community of observers, professionals, students, amateurs, build a continuous light curve or a mosaic of spectra is a test of our cooperative reflex. Sharing methods, posting null results, aligning filters and clocks, inviting others into otherwise closed loops. All of that is a rehearsal for bigger scientific tasks and a reminder that our best instrument is social, not only optical. If we can hear a whisper because we distributed the listening, then something in our common house is working the way we like to say it does. The visitor helps us prove it quietly. Philosophically, a dot of light on an unbound path reframes our location without drama. We are not a basin where things settle. We are a crossing where lanes meet, a place transparent enough for messengers to pass through without stopping. This is not smallness as a rebuke, but smallness as design, a system open at the edges, exchanging seeds and shards with neighbours, learning by interception. When you look at the spectrum and see lines and slopes that match what we have learned to read across decades, you are watching a common physics that does not care about our boundaries. When you see a deviation, you are witnessing a useful disagreement, an expansion of the vocabulary we use to talk about stones and ices under stars. And there is the simplest home truth: measurement creates kinship. You point, record, subtract, divide, fold, fit. You compare to standards your predecessors agreed upon. You draw a curve and add it to those drawn in years you didn't live. The line sits beside theirs without apology. Whether the visitor matches or departs, your curve belongs to the same score, and our we expands a little to include one more sentence from a sky that is not ours alone. The comet tells us about home by standing next to it and letting us measure the difference, which is how families work when they're honest. Not by insisting on sameness, not by treating difference as threat, but by learning, detail by detail, what can be counted on and what can be varied without breaking the shared language. From that language, both here and elsewhere, we build the next question and the next instrument and the next night's plan, and that plan is, in the end, a way of caring for our home that feels practical. Keep listening, keep comparing, keep writing down what the light says when dust and ice talk under a star. Contact is not a handshake or a headline. It is the moment when a pattern refuses to stay hypothetical. You have a model that predicts a rise here, a dip there, a small delay between gas and dust, a jet that should rotate into view after a certain fraction of a turn. You set thresholds and priors so you cannot be easily fooled. Then the sky, which owes you nothing, draws the same shape you drew on paper. The light curve crest lands within minutes of the forecast. The faint CN band lifts by the amount the G-factors and geometry said it should. The jet spoke appears where the synchron map said it would. This is not drama, it is alignment. The The room does not cheer, it exhales because recognition has a quieter sound than surprise. Mathematically, this moment has names. A base factor rises above interesting and into decisive. A likelihood ratio says the periodic model beats the straight line model by odds you would stake your sleep on. A matched filter, built from last night's suspected jet profile, slides across tonight's difference images and returns a peak exactly where the rotation phase placed it. A cross-correlation between gas and dust curves shows a lag that remains when you change binning, when you swap reference stars, when you throw away the noisiest frames on principle. The significance is not a single sigma, it is a pile of unexciting agreements that together climb past your bar for calling something real. Physically, contact means coherence across instruments. The photometer's gentle brightening is mirrored by spectrograph's rising OH. The polarimeter shows a small dip in polarization at the same time the colour reddens. The radio dish measures a slight widening of HCN lines that matches an outflow speed increase inferred from optical line widths. The tail image gains a new stria whose age, computed from its distance as a synchrone, points back to an outgassing surge timed by the light curve. Independently reduced, differently calibrated and separated by continents, the data stop contradicting and start conversing. When two teams predict, without conferring, that the next favourable hour will show the same motif and it does, the word contact earns its lowercase c. There is also a geometric flavour to this sense. In a state space of plausible explanations, instrument, atmosphere, geometry, object, your posterior mass migrates away from the first three and settles on the fourth. A cloud would have raised the background in both filters, it didn't. A guiding error would have smeared stars more than coma, they didn't. A phase angle change would have brightened everything smoothly. The change was structured. The simplest surviving narrative is that the comet itself changed in a way consistent with being a small, sunlit factory. Occam is not a poet, but he tells you when meaning has fewer moving parts than coincidence. You verify, as always, by trying to break the feeling. You re-reduce the same night with a different aperture scheme, and with PSF fitting instead of fixed radii, the shape persists. You swap the set of comparison stars. The baseline shifts slightly, but the curve's architecture stays. You apply the same pipeline to a control field observed nearby. It stays flat. You blind the timestamps and ask a colleague to guess the period from a scrambled sequence. They return a number within error. You run injection tests, simulated signals added to raw frames, and confirm that a signal of the measured size would have been recovered with the measured uncertainties. Each failed attempt to disprove yourself is not stubbornness. It is how you earn a reason to believe. Contact is often small, a 0.04 magnitude modulation that repeats with a period that drifts by a fraction of a percent across a week. A CN/OH ratio that sits a little higher than the median of solar system comets and stays there night after night. A sodium line that appears just above the limit and 3 rotations later appears again with the same relative strength and width. These are not discoveries in the noisy public sense. They are confirmations that this visitor has a personality, and that your instruments, calibrated against distant suns and dense math, are sensitive to personalities. Sometimes contact is a delay that matches a mechanism. Gas increases first because sunlight has reached the vent. Dust follows after minutes because grains need acceleration to clear the nucleus's weak gravity and enter the aperture. The measured lag matches the drag you'd expect from the gas production rates you inferred, and a simple ballistic model, no tricks, no hidden knobs, reproduces the timing, or the reverse. A dust-rich outburst brightens the continuum without a matching gas rise. Polarization and colour confirm larger grains, radio lines stay flat. The consistency across these tracks is not a coincidence. It is a causal chain supportable by order of magnitude physics that fits on a napkin and still meets the numbers. Cause-meeting effect at the measured tempo is a kind of conversation. There is an auditory metaphor that becomes literal in analysis. You build a template from the suspected rotational modulation, convolve it with window functions for each observatory's gaps, and ask whether the combined gappy instrument could have produced a clean tone by accident. The answer is not with these gaps, not at this amplitude. You tune the template slightly, letting the period drift linearly to mimic torque. The fit sharpens and the residuals whiten. Numbers sing when a model gains you simplicity in the leftovers. It is the soft click of a puzzle piece that finally sits without rocking. Spatially, contact arrives as symmetry that shouldn't hold if artifacts were running the show. A jet seen sunward in the morning rotates tailward by the evening, according to the spin axis you estimated from last night's polar plot of azimuthal brightness. The measured position angles line up within a few degrees. A faint anti-tail appears on the predicted date of orbital plane crossing, and fades as the geometry moves on. Its surface brightness gradient matches the Syndine set labelled by the large grain beta you measured from curvature. These are not graphical coincidences. They are the geometry and dynamics being read correctly enough that prediction becomes observation with shorter and shorter sentences. Language enters when you can summarize without hedging every verb. The nucleus rotates in 5.10 plus or minus 0.075.10 plus or minus 0.07 hours, with a small linear spin-up of plus 0.003 plus 0.003 hours per day, likely due to sustained outgassing torque. Water production increased from 1.2 to 1.8 times 10 to the 27th power, 1.8 times 10 to the 27th power, 10 to the 27th molecules per second to the minus first power over 3 days at 1.2 astronomical units with CN tracking at a constant ratio, QCN/QOH equals 0.003 plus or minus 0.0005. Polarization at phase angles 35 to 55 degrees followed the standard comet curve, but sat lower by 1 to 2%, consistent with a higher fraction of compact grains. Each sentence is a small claim tied to a plot, a residual, and a calibration. Together they form a paragraph that sounds like understanding, because you could delete any single sentence and the others would still stand. Redundancy is how meaning becomes robust. The body's response becomes part of the evidence. Your shoulders loosen when the period lands where the periodogram said. Your breath slows when the folded light curve tightens as more rotations are added. Your notebook handwriting shifts from cramped to spacious as the need to annotate every uncertainty gives way to writing down the few that matter. This is not mysticism. It is a trained animal, a human brain, recognizing a pattern and turning down the vigilance that random data requires. You don't rely on that feeling for proof, but you notice it, the way a pilot notices an engine's vibration returning to its customary pitch. Contact also means reproducibility that ignores personality. A different team using a different reduction recipe reports the same period within errors and the same amplitude within a few hundredths of a magnitude. A space-based spectrum measures CO2 where your ground-based IR could not, and the ratio to water aligns with what your visible bands implied indirectly through oxygen lines. An amateur network's nightly averages, noisy but plentiful, trace the same slow brightening that your sparse professional points did. When the results survive translation between instruments and styles, the message is no longer attributed to our pipeline or our site. It becomes a tribute of the comet. What contact is not? It is not certainty about everything. It is not permission to tuck speculation under data's coat. It is not immunity to later revision. It is a state in which the simplest, most economical description of the measurements includes the comet as an agent in its own changes, not the sky or the sensor. It is the minimum completeness that lets you add the visitors' numbers to tables that outlive the night and hold up years later without apology. It is the point at which you would be comfortable letting someone else schedule their telescope time on your predictions, and you would accept responsibility if those predictions failed. there is a practical next step that Contact licenses: forward modelling without embarrassment. You take the measured spin state, jet geometry and production rates and propagate them one rotation into the future to choose slit orientations, filter cadences, and exposure times that emphasize what's informative. You plan a polarization sweep across a specific phase angle range, where your current curve is sparse because the rest of the curve just held steady enough to make that gap meaningful. You request a millimeter tune for a line that sits right where the swings effect will increase pumping next week because tonight's heliocentric velocity made the visible bands unusually weak. These are not leaps of faith. They are bets placed with house money, evidence that just paid out. Contact makes even science informative. If a predicted repetition fails on schedule, you look to torque or geometry first, not to cloud or clock. If a gas band refuses to rise after dust brightens, favour crust collapse or large grain ejection without volatiles rather than calibration slip. If the anti-tail does not appear on the expected day, you check plane crossing ephemerides and beta distributions before you blame the flat field. You have earned the right to consider physics before error because you did the homework that pried those two apart last night. Humility remains the posture. You keep the audit trail intact. You post the pipeline and the raw frames. You record the weather's moods and your own choices. You mark which figures are exploratory and which are claims. You keep updating the orbit with non-gravitational terms only when the residuals demand it, not because it feels satisfying. You welcome a null from another team that trims your amplitude by a few hundredths and tightens your error bars. Contact is maintained by this ethic. It decays if pride outruns calibration. On the human side, the tone of the room settles into a different quiet. People stop making suggestions every 2 minutes and start making notes every 15. The radio chatter between sites shortens to timestamps and single numbers. The cadence of exposures becomes a steady drum that invites longer thoughts, like what mixture of grain strengths would produce the observed lag, or how the pole orientation implied by jet drift compares to stable equilibria for tumbling bodies. The work never becomes grand, it becomes precise, and precision is its own kind of peace. And if you allow yourself a small private image for this very technical thing, it is this. Somewhere between the lines and the slopes and the fits, the visitor stops being a streak or a smudge and takes on the consistency of a voice you recognize, not a language you understand in words, but a cadence you could pick out in a crowded room. It speaks by keeping time with your predictions, by bending ratios the same way twice, by leaving a thin ray of dust where celestial mechanics said a ray should be. That is contact in this domain, the joining of expectation and arrival, the quiet handshake between model and measurement that says you are no longer just looking at light. You are listening to a presence that keeps its own time and, for these nights, is willing to let you keep it with them. Departure begins long before the object is gone. It begins when the nightly plots stop climbing and settle into a slow, dignified decline, when exposures lengthen not out of ambition but out of necessity, and when the object's name moves from the top of the observing queue to the middle, and then to the margin, not out of neglect but because the sky is full. The coma thins first. Profiles that once fell like a steady one over row start to sag. The inner few arc seconds no longer demand wide apertures. Jets that once carved tidy fans blur into a uniform haze that looks more like memory than geometry. Gas lines, which had been patient narrators, lower their voices. O softens until it shares its window with the night sky background without argument. CN keeps a last quiet thread. C2, once confident, becomes a rumour that calibration can still respect but no longer celebrate. The tail keeps its shape longer than its shine, like chalk lines after a game that the wind takes its time erasing. Synchrones march outward but lose relief, as if the sculpting lamp was dimmed and the stage crew carried away the props one by one, fading teacher's scale. Exposure times creep from seconds to minutes to tens of minutes, and in the creep you learn what sufficient really means. Read noise, once negligible, takes its seat at the table again. Cosmic rays that a Sigma clip would have dismissed casually now lean in close to your faintest features and ask to be believed. Background subtraction becomes a study in kindness. Too aggressive, and you sand away the last truth. Too gentle, and the sky drowns what you came to hear. You reduce in pairs and trios, cross-checking apertures and annuli, letting the quieter pipeline lead when the assertive one starts to decorate the noise. You accept that stacking is no longer a luxury but the only way to keep the line on the page. Patience that felt like a virtue earlier becomes a craft. Choose dither patterns that spread the scars, schedule calibration stars as often as science frames. Give up narrow slits for wide ones when flux, not finesse, is the currency. Geometry keeps offering small gifts as the brightness ebbs. Phase angles sweep through ranges you did not have at peak, and the polarization curve, thin with points before, fills in a few degrees that make the model sit a little flatter. The Earth crosses the orbital plane a last time, and an anti-tail that would have stolen the show weeks ago now appears as a faint, exquisite line, a proof of concept rather than spectacle, still valuable because it nails the beta distribution where other methods are fading. A solar wind sector boundary walks through the heliosphere and snaps the ion tail cleanly even at low surface brightness, and the timing against upstream monitors writes one more timestamp on the visitor's plasma diary. You harvest these with a gentleness that suits their scale, content that small truths gathered late are still truths. Orbit solutions do not care how bright the source is, a position is a position. Even as photometry becomes hard, astrometry can persist. The field stars do their steady work. The centroid routine remains honest to 1/10 of a pixel when you treat it with respect, and each dot added to the skyplane plot tightens non-gravitational terms that would otherwise drift as the comet's own breathing changes its gait. If the nucleus is still venting enough to matter, the residuals will arc, and the A1, A2, A3 parameters will creep to the values your physics expects. If activity has fallen below dynamical relevance, the fit relaxes and gravity reassumes its clean lines, a different kind of goodbye. Less personal, more classical, still instructive. Radio lines are stubborn and generous in this phase. An optical spectrograph's band may sink below detectability, but a millimeter receiver can still hear HCN whispering, and the width of that whisper says the outflow speed has cooled with distance. Integrations lengthen, beam maps widen, and the product of time and care is the last few points on a production curve that might otherwise break awkwardly. Thermal infrared sometimes offers a coda. 2. The dust that no longer shines well in reflected light still glows with its own mild heat, and a 10 micrometer silicate feature, low as it is, can be measured against a cleaner mid-IR sky to fix a crystalline fraction that had only been bracketed before. You accept the trade, fewer wavelengths, longer exposures, narrower questions, answers still welcome. On small telescopes, the long goodbye is social. The object moves into hours when students can observe after classes, when amateurs can give a clear Saturday to a single target, when a teacher uses the comet to show a room that not everything in space is permanent. 100 short exposures from many places, combined with discipline, produce a single dignified point with error bars that deserve to be on the same plot as a large observatory's. You build that point and give it away. The light curve gains one more night of continuity. The period, if still present, is confirmed faintly. The tail's profile, though barely above background, still slopes the way physics prefers. Humility, technical and human, makes late data good because late data cannot be collected without it. Archiving becomes the main verb. You review headers, repair fits keywords, a sleepy script left blank. Attach weather notes that mattered once and will matter again when someone else wonders why a night was noisy. You calibrate your reduction pipeline's last iteration against the penultimate one and write down what changed so that a number from this week can sit in the same column as a number from 2 months ago without apology. You mint DOIS for reduced product so that careful work does not vanish into forgotten directories. You add plaintext README files that explain folder names in sentences a future reader will understand. This is not paperwork. It is the craft of making measurement survive its moment. Writing is part of staying. You start drafting figures that do not require defending with a speech, plots that tell their own truth in lines thin enough for error bars to breathe. You choose a style that will look ordinary in a decade because ordinary ages better than clever. The captions are complete without being proud. What instrument, what filter, what aperture, what calibration, what standard, what uncertainty, what was done when something failed, what was not done. You write methods like recipes tested by another person in your group who does not love your code and therefore can find your shortcuts. You identify the places where interpretation begins, mark them, and omit adjectives that perform certainty you do not have. In late light, honesty is the grippiest surface for the future to hold. For some, the long goodbye is logistical. Proposals close while the comet still whispers. You decide whether to ask for time next semester knowing the object will be fainter by an order of magnitude, or whether to pivot to analysis while the echoes warm. You triage unfinished questions. Is the rotation state really drifting, or was that an alias? Did the CN/OH ratio truly sit above typical, or did geometry bias the slit? Were the jets single or multiple? And can the late synchrones resolve that ambiguity? You give the answer each deserves. One more night or none. One more cross-check or a quiet line that reads inconclusive. Saying we don't know comes easier. When the curve as a whole is strong, ignorance is not a hole, it is a marked path you did not walk this time. Emotion is not data, but it passes through the room and should be named so it does not act backstage. The early adrenaline of discovery, the middle satisfaction of models meeting measurements, gives way to a steadier feeling that is not loss so much as completion. People close tabs. The chatter on the shared channel slows from paragraphs to numbers to timestamps. A last clear night goes to a different target, and nobody feels disloyal. The comet occupies a new place, not the screen, but the schedule for the paper, the to-do list for the archive, the figure arrangement in the draft that will teach someone else what you heard. The work remains a community act, simply in a different tense. Even as the flux decreases, the physics becomes bolder in one way. Exponents and proportionalities reveal themselves because noise does not tempt you toward flourishes. Water production versus heliocentric distance fits a slope you can quote without blushing. The dust proxy AFR settles to a curve that matches a simple outflow story. Polarization points sit near a standard track, neither heroic nor disappointing, and that ordinariness is power. It says the visitor is neither an outlier demanding exceptions nor a ghost that only looked real in bright nights. The tail's curvature, even at low contrast, holds a beta range you can put into a table. The non-gravitational parameters solved with and without activity bracket the truth. Late measurements, modestly posed, carry out size weight because they are not vying for attention, they are closing loops. Comparisons bloom as the data go quiet. You overlay curves from other comets at similar distances and see families, not just cases. Some lines run nearly parallel, shared thermodynamics under different suns. Some diverge early and converge late, surface layers yielding to deeper, more typical ice. Some stand apart cleanly, reminders that variety is not noise but character. The interstellar label matters less in this plot than the behaviour that label brought into view. Our own comets look less provincial beside it. The visitor looks less exotic beside ours. The graph is not an award ceremony. It is a seating chart where everyone's place makes sense. Teaching follows naturally. You turn the campaign into an exercise for a class. Here are raw frames, flats, darks, a script, and a rubric. Students reproduce one figure, a light curve for a single night, a production rate from a band, an image subtraction that reveals a jet. They write about their choices and uncertainties. They see that subtlety is not code for fragility. They learn that well-kept notes beat cleverness. The comet becomes a lab manual in motion, a rare thing. a piece of the sky that can be graded without being diminished. Instrument people take notes for the next build. Which modes were used most, which filters saturated, which readout speeds earned their keep, which calibrations proved brittle. They write wider slits for faint phases in a margin, more stable flats in the red in another. They consider a polarization module that rotates faster between angles, a software wrapper that logs weather metadata automatically instead of trusting memory at 3 AM. Hardware that learns is a quiet legacy of any target that asked for more than light and delivered. The visitor leaves the instrument better for the next visitor. Some nights, late, give you a last small surprise. A brief outburst raises the continuum by 1/10 of a magnitude and then subsides, leaving a crisp new synchrone that your model will use to time the event. A sector boundary arrives earlier than expected, and the ion tail kinks where you had pointed a camera more out of habit than hope. A reference star that has been steady all month flickers and teaches you one more time to use at least 3. These are small graces, reminders that the sky stays lively even when your object is tired, that vigilance remains a kindness, not a demand. Eventually the data sit. The comet is in the morning glare or below a horizon, or simply too faint for the gear on hand. You watch it with software instead, propagated position stepping out, magnitudes estimated beyond practical reach, a line on a chart that continues because the mathematics does, not because the photons do. There is honesty in that too. Prediction belongs to physics, observation belongs to weather and budgets and sleep. You respect both by not pretending the first is the second. The last act of a good goodbye is making the work easy to meet again. You place the reduced sets where search engines can find them. You give a short, non-technical summary somewhere public so that someone who saw a headline months ago can learn the end without learning jargon. You answer a student's email with a link and a figure and a sentence that says, "Yes, you can use this in your project and here is how to cite it." You circle a conference date on a calendar and draft the slide where the visitor's curves slip into a larger plot of many equal in dignity, stronger together. The comet has travelled on, the work has not. If you listen late, you can still hear it. Not the specific period or the exact ratio, but the cadence of a process that repeated often enough to become a habit. Point, wait, measure, subtract, compare, predict, confirm, archive, explain, and then hand the light to the next pair of eyes. The visitor leaves that cadence behind, held now by people and code rather than by dust and gas. And that is not loss. It is the shape that remains when a moving thing has passed through, and the room, a little changed by having kept time with it, continues to keep time. The sky will offer another traveller, and the instruments will be ready a little earlier, the checklists a little quieter, the thresholds a little wiser. The long goodbye is therefore not a curtain, it is a practice, a way of letting something depart without letting the learning decay, a way of holding a fading signal with enough gentleness that when it finally sinks into the background itself feels more like a place you know how to read. If you're still with me, somewhere between waking and the soft edge of sleep, thank you for travelling this whole arc, from the first quiet preparations to the slow fade of a visitor that will never return the same way again. We listened to dust and gas learn our sunlight, watched numbers turn into meaning, and let patience become a kind of language. Out there, 3I/ATLAS keeps going, carrying a pocket full of foreign weather into deeper dark. Down here, you and I keep a small promise to notice, to record, and to be changed a little by what we notice. That is enough for tonight. If this journey eased your mind or lit a gentle spark, I'd love for you to subscribe and tap the bell, so these calm expeditions can find you again when the world feels loud. Leave a simple comment, anything, even a good night, or share this with someone who needs a quiet sky. Your presence here is what lets me make these long, unhurried voyages. Before you drift off, take one unforced breath in and an even longer one out. Let the room settle. Let your shoulders drop. Notice that the same laws that guide a comet past the sun guide your breath past each thought, rising, curving, falling, gone. Somewhere in the distance, a sensor ticks, a graph steadies, a dome closes. Somewhere closer, your eyelids find their own slow cadence. If your mind offers one last question, set it gently on the bedside table with your keys. There will be time for questions tomorrow. For now, there is only the good sky and the soft weight of blankets. When you wake, the visitor will be a little farther away and we will be a little farther along. But the trail we left, figures, notes, and the simple memory of listening will still be here. If you want more journeys like this, more star-quiet stories, more careful wonder, subscribing is the easiest way to keep our paths aligned. And if this helped you rest, a like tells the algorithm that silence has value too. For those who have supported, commented, or simply let this play as the room dimmed, thank you. You are the reason these long-form lullabies exist. Now close the ledger, dim the lights, and let the night finish the sentence for us. The comet continues, the data rests, the heart slows. May your dreams keep an orbit that brings you back to calm, and may the morning find you with a little more room inside for awe. Until our next quiet crossing among the stars, good night, sleep deeply, and keep listening for the softest signals of your own clear, patient light.